Welcome everyone. We will start with the inaugural session now. So I request Professor Bharti Gondalekar to take it from here.
Yes, sir. Thank you. Good evening, everyone. Hope I'm audible to all.
Good evening.
Yes, ma'am.
Yes, ma'am.
Yeah.
A warm welcome to all the esteemed dignitaries who have joined us on this online platform. Chief guest of today and keynote speaker, Dr. Debradat Datta, Principal, Dr. Rakesh Himte sir, Dean Academics, Dr. Vikas Gupta, HOD XTC, and Coordinator, Dr. Amruta Ruperi. We at Vidyavardhani's College of Engineering and Technology are honored by your august presence. Department of Electronics and Telecommunication has organized a 6-day online ATAL FDP on quantum intelligence. Quantum intelligence is the powerful fusion of quantum computing and artificial intelligence. It is further frontier where quantum computing's unique processing power meets AI's analytical capabilities, aiming for a breakthrough in complex problem-solving capabilities. Let us all grow by sowing the seed of knowledge. I, on behalf of the department, would like to welcome all the participants who are curious and enthusiastic enough to learn, unlearn, and relearn the blends of technologies. And now, let us not forget that learning always begins by invoking the blessings of Ma Saraswati, the goddess of knowledge. Shraddha ma'am, could you please take over from here?
Yes, ma'am.
या कुन्देन्दु तुषारहारधवला या शुभ्रवस्त्रावृता या वीणावरदण्डमण्डितकरा या श्वेतपद्मासना या ब्रह्माच्युतशङ्करप्रभृतिभिः देवैः सदा वन्दिता सा मां पातु सरस्वती भगवती निःशेषजाड्यापहा शुक्लां ब्रह्मविचारसारपरमा
There's some puja they were doing. Puja.
वीणा पुस्तकधारिणीम् अभयदा जाड्यान्धकारापहा हस्ते स्फाटिकमालिकां विदधतीं पद्मासने संस्थितां वन्दे तां परमेश्वरीं भगवतीम् बुद्धिप्रदां शारदाम्
May the divine energy fill our hearts with knowledge, understanding, and wisdom. Moving further, with immense pleasure, I request Dr. Amrita Ruperi, HOD XTC, and the coordinator of the course to brief us on today's topic, quantum intelligence.
Thank you, Bharti Madam. Am I audible?
Yes, ma'am.
Okay, good evening all those who are present in this meeting. I, Dr. Amrita Ruperi, Coordinator and Head of Electronics and Telecommunication Engineering Department, welcome you all for the inaugural function of 1 week AICT-sponsored ATAL Faculty Program on Quantum Intelligence, exploring the convergence of quantum computing and artificial intelligence. This faculty development program is organized by Department of Electronics and Telecommunication Engineering of Vidyavardhani's College of Engineering and Technology. It's our honor that we have with us keynote speaker, Honorable Dr. Debabrat Datta, professor and former nuclear scientist, former head Radiological Physics Advisory Division, Bhabha Atomic Research Center. I welcome you, sir, for the inaugural function of Faculty Development Program, and thank you for accepting our invitation.
Yeah.
I would like to
Thank you,
welcome
madam.
our principal. Okay, sir. I would like to welcome our principal, Dr. Rakesh Himte, Dean of Academics, Dr. Vikas Gupta, faculty members, and all my dear participants. Over the past decades, artificial intelligence has gone from an experimental science to global force, which powering industries, driving research, and shaping how we live, work, and understand the world. Quantum intelligence can make computers much faster than they are today. It may help scientists study molecules in just a few seconds. Individually, these two fields are extraordinary, but together they have the potential to redefine the limits of human capability. Considering these two emerging fields and their potential, the objective of these faculty development programs are introduce the fundamentals of quantum computing and AI through practical approach to enhance foundational understanding. Familiarize participants with qubits, quantum gates, and construction of basic quantum sockets. Provide insights into key quantum algorithms and their world application. Highlight recent developments, research trends, and technological advancement in quantum computing and AI, and also identify and explore potential research area, collaborative projects, and grant opportunities. The true power of quantum intelligence is not merely in achieving faster results, but in reshaping our fundamental relationship with the information. The choice we make today will shape the digital and scientific landscape for generations. So considering this and taking the opportunity, I would like to thank our management, Principal Dr. Rakesh Himte, for their motivation and guidance. I would like to thank deans, HODs, all the faculty members and staff of department and their supports. I appreciate the efforts taken by co-coordinator Ms. Shaista Khanam, Ms. Neha Garat, and all the faculty members. I would like to thank all the participants for registering for this program. I hope you all will enjoy all the sessions. Thank you all and happy learning. Thank you. Over to Bharti Madam.
Yes, ma'am. Thank you so much. Moving further, deep insights regarding the contents of the course would be shared by Ms. Shaista Khanam, Assistant Professor and the course co-coordinator, sorry.
I'm audible, ma'am?
Yes, ma'am.
So, respected dignitaries present, distinguished keynote speaker Dr. Datta, Principal Dr. Rakesh Himte sir, Dean Academics Dr. Vikas Gupta, HOD and Coordinator Dr. Amrita Ruperi, colleagues, and dear participant. A very good evening to everyone. It gives me immense pleasure to briefly introduce the academic content of this AICT sponsored ATAL Faculty Development Program on Quantum Intelligence, exploring the convergence of quantum computing and artificial intelligence. This 6-day FDP has been carefully designed to take participants on a structured journey from foundational concepts to advanced applications in quantum technologies. We begin on day one with a strong foundation in quantum mechanics, quantum gates, and quantum algorithms, followed by the session on quantum workflow, modeling, and simulation to provide practical exposure to quantum systems. As the FDP progresses, participants will explore quantum computing simulation, acceleration, superconducting qubits, and emerging quantum technologies, effectively bridging the theoretical concept with the real world implementations. Session on quantum machine learning, quantum transformer, federated learning, and quantum AI application emphasize the collaborative role of artificial intelligence in enhancing the quantum computing models, algorithms, and decision making processes. This FDP also covers the important applications areas such as quantum cryptography, quantum communication networks, quantum teleportation, and quantum safe security from an industry perspective. Concludes with an assessment and the valedictory session. So, with eminent experts from IIT, CDAC, ISI, IBM, Deloitte, and leading research institutes, we are confident that this FDP will academically enriching and future focused. So, I sincerely hope all the participants will make the use of the most of this learning opportunity. Thank you so much. Over to you, Bharti ma'am.
Thank you, ma'am. Now I request our Dean Academics, Dr. Vikas Gupta sir, to share a few words on this occasion.
Thank you, Bharti ma'am. Why this
So
echoing?
it's echoing.
Let me check. Hello.
So it's echoing
Okay,
again.
So if you are logged on from two devices, please turn off one of the device.
I I think I did it from both app and browser in the same device. So
Sir, switch from one.
Close one and just continue with the other one.
hello. Sorry. This is this I'm not getting able to get. Hello. Now it's okay.
Yes, sir.
It's fine.
Yes.
Okay, fine.
Okay, sir.
Very good evening, everyone. Respected dignitaries, the esteemed resource person, dear colleagues and participant. A very good evening to everyone. It gives me great pleasure to welcome you all to this AICT online ATAL Faculty Development Program in the domain of quantum technologies. I sincerely thank AICT and the ATAL Academy for supporting this program on a domain that is poised to redefine the future of science, engineering, and technology. I'm really glad that in the pursue or in the continuation of excellence by the EXTC department of VCET, they selected this topic, and this is really very good. Though it looks like that this is a bit advanced, and the EXTC people should not take interest. So this is basically interdisciplinary topic, and I really congratulate the team to take this challenge. And I see in the galaxy of experts from various areas, and I'm very sure that this program will be huge success. As far as quantum technology it represents a shift in the area of quantum computing, secure communication, sensing, next generation materials. That is a good thing that is coming up, and our students and faculty should be aware of the materials for the electronics. For us, it is essential to understand these emerging technologies, and as a academic persons, we should integrate them into the teaching research, curriculum development. As we have got autonomous now, we have to do it in the line of NEP 2020. I hope that for all the computer light branches, including other core branches also, will integrate this quantum technologies domain in the syllabus. These FDP, actually, the faculty members will get the benefit of the getting some foundation knowledge. Is a new area. Some of you may be aware of that, but I hope most of you, those who got interested in this, they really want to know new. They will come to know the current research trends, and the utmost part is the practical insight of the quantum technologies. Theories, we can see, we can have some kind of a courses, but I seen the course is designed to give the simulation tools and practical insights of the quantum domain. And the participant definitely should explore the interdisciplinary research and some innovative pedagogy, because we are learning some FDPs, we are doing something, but we should learn simultaneously how to deliver, what kind of pedagogy we should have in this kind of advanced subjects. This is definitely cannot be a traditional teaching for us. And also we can, as a group, we can do some collaborative projects. So once again, I take this opportunity to appreciate the efforts of the FDP coordinator and the organizing team for their dedicated work. I've seen they're working day and night, and they're present in the college. So this is really encourageable, and that will give a lot of strength to the team and the students. So also at the for the participants, I really want that they should actively engage. They should not see like that we are attending FDP. You actively engage, interact with the experts, connect with the experts, and best make the best use of this FDP. So I wish this FDP very success and hope it continues meaningful in building what I may call it like a quantum ready faculty and a quantum ready institution. So thank you. I wish you all a fruitful program. Thank you very much.
Thank you, sir. Thank you very much for your words, those kind words. Uh, Now, moving further, today's keynote speaker, as you all know, is a nuclear scientist, an outstanding and multi-award winning personality. I request Mrs. Shaista Khanum to introduce our chief guest, Dr. Datta.
Yes,
Over
ma'am.
to you, Shaista ma'am.
Yes, ma'am. So, Dr. Datta is a nuclear scientist who retired from Bhabha Atomic Research Center, Mumbai, after contributing a commendable service for a period of 34 years in the field of nuclear science and technology. At present, he is working in the capacity of professor in the Department of Information Technology and Joint Research Director of Research and Development of Heritage Institute of Technology, Kolkata. He is also contributing to his expertise as a principal scientist in Automatic Chemical Element Detection Private Limited, Gurgaon, Delhi. He is associated with the Department of Mathematics as adjunct faculty of SRMIST, Chennai. His academic excellence are MSc Nuclear Physics and MPhil Nuclear Physics from Calcutta University, graduate in Nuclear Engineering from BARC Training School, Mumbai, and PhD in Science from Mumbai University. He has worked in many fields of science and engineering and developed many software for use in nuclear technology and regulatory activities. He has been deputed to International Atomic Energy Agency IAEA, Vienna, Austria, to test the quality control of RAIS software, and also in Indonesia in 2017 to strengthen the medical physics education by e-learning system software Ample. He is a receptionist of Eminent Scientist Award. The first award is Millennium Plaques of Honor from Indian Science Congress Association, Group Achievement Award for Science and Technological Excellence from BRC, Jal Vigyan Puraskar from ISH Journal of Hydraulics, and Meritorious Award from many scientist societies. He has supervised, co-supervised 10 PhD theses, 150 MTech theses, executed 12 BRNS projects as a principal collaborator. He has got 3 patents for developing masks as a data analysis of COVID-19 and smart medical basket for hospital management. He has got more than 350 peer-reviewed international journal publications, 200 publications in national conference, 40 book chapters, and 130 invited talks and keynote delivers at various academic institutions, national, international. He is editor and editorial board member of many international journals. He is a life member of many international and national scientific bodies. So, sir, it is truly an honor for us to have a such distinguished scientist, academician, and researcher with us today. His decades of contribution to nuclear science, technology, education, and interdisciplinary research are both inspiring and impactful. On behalf of organizer and participant, I extend a very warm welcome to Dr. Datta sir and request him to kindly take the session forward. Thank you so much, sir.
Thank you, madam, for your nice word. And
Thank you.
I'm very simple, not the way you mentioned, but let me see that how I can take the session. Okay. Thank you.
Thank you, sir.
So can I start, or anybody else is there to speak further?
Before we start the actual session, let me just put forward the vote of thanks.
Okay.
Good evening, everyone. Organizing any event is efforts of many people coming together. And I take this opportunity to thank all of them who has helped us in organizing this ATAL FDP program. Myself, Dr. Ashish Vanmai from EXTC Department of VCET Vasai. This event is possible because of the efforts taken by many people. First and foremost, I would like to thank our management and principal who has always encouraged us to organize such events. We also thank AICT and ATAL for giving us the permission for this online FDP. Especially to mention the coordinator, Dr. Amrita Riperi, and co-coordinator, Shaista Khan and Neha ma'am, who has worked tirelessly along with the all faculty members of EXTC department to make this particular event a huge success. Special thanks to Dr. Datta, who is chief guest for today's inaugural function and also the keynote speaker, and all the other speakers who are going to join us in this 6 days time for accepting our invitation and who are going to share their knowledge with all of us. The success of any event or program depends on the participants. And I'm very glad that we have received a huge response for this particular FDP. So I also thank all the participants who have shown faith in us. And I hope that this 6 days journey is going to be fruitful for everyone. So with this, I conclude my vote of thanks and I will be handing the session to Professor Datta. But before that, let's have a group photograph as our memory of this inaugural session. So I request all the participants to kindly turn on their cameras so that we can take a group photograph and then we can move further for the first session for the today. I'm requesting all the participants to kindly turn on their cameras. Yeah, thank you everyone.
Okay.
Now I request Dr. Datta to start his session.
Okay. So again, that the good evening to all the participants. And first of all, my word towards the team for arranging such a nice ATAL FDP program on quantum computing. Basically, the merging of quantum computing and artificial intelligence, we call together as a quantum intelligence, right? But alternately also, whenever we are mixing that the quantum computing and artificial intelligence, we call it as a professionally artificial general intelligence, or AGI in short. So from that angle, it is really very important to consider the future computing and future intelligence with the help of the combination of the quantum computing and artificial intelligence. Of course, as Dr. HOD has mentioned also, that teaching of the quantum computing is not grown traditionally, but we require to consider that the depth of the teaching, not towards the only blackboard teaching, but to some extent we have to implement the practical part also. I mean that the hardware concept also is required to consider in that teaching. There are a lot many softwares are available, but sooner or later, with the help of quantum hub already implemented in Mumbai IIT, we will be used for this kind of many hardware implemented circuit, which will take all the participants as well as the students to implement the quantum computing and to solve the complex problem which cannot be done by the classical computing. So with the help of simple few words, let me present my uh, presentation, and you can take me that you can tell me that whether it is shared or not. Okay, I am sharing my screen. So this is the screen I have shared. Hope it is there. Uh, is my screen is visible to you?
Yes, sir.
Okay, so I can present from
Um,
here. So
yes.
Your screen is visible. Yeah, now it's full screen, sir. Thank
yeah,
you.
Yeah.
okay. So my session will start from here, and the topic which I have kept, because it's the first session, so we need to have the knowledge of quantum mechanics. So that is why topic is that the fundamentals of quantum mechanics. Then we'll proceed to the quantum gates and quantum algorithms. So from this concept, my content of presentation will be like this: is a quantum computing. Of course, you would like to see that what is the quantum computer, how does it work, and fundamentals of quantum mechanics should be known first, because we know that the physics people always known about the quantum mechanics but not quantum computing. But since it is a concept is coming to the engineering branch, so definitely the quantum mechanical concept is required to know. Okay, because the whole quantum computing will be based on the quantum mechanical concept, mostly the algebra part. So that's why we have put the Hilbert space and linear algebra, and using that we will be designing some kind of hardware which will be called as a quantum gates, quantum circuit, and then which will be followed by some quantum algorithms. Then we will know that what kind of problems really we can solve, and we will conclude the session later on. Okay, so this is the structure of a quantum computer, and if you look at it, is totally different. But to uh, understand the whole procedure, you can see that the quantum computer is basically sandwich between two classical computers. Okay, that means the information you are feeding to the quantum computer from a classical computer, and information extracted from quantum computer you are dumping into the classical computer. So therefore, we say that the quantum computer is basically always a hybrid concept because it is sandwiched between two classical computers. Why does it so? Because it is very simple that if you look at the classical computer, we feed the information in a usual language or human understanding language, but inside the classical computer, this is a assembly language takes place. Computation takes place with the help of mnemonics and macro processor, and then output is coming again to the user interface. Okay, user understanding. Similarly, in the quantum computer, the information feeding by the classical computer is the human understanding, and information extracted from quantum computer is also a human understanding. So therefore, we need to know that a quantum computer is basically a structure. On the right hand side, I have shown that we have a control processor, quantum substrate, because this kind of hardware, when you do, you will see it is different from the classical computer because it is not a single desktop or this. A desktop itself is having a lot of layer. So that's the meaning of that. You submit a job, then job queue will be there, and most of the job will be submit to the cloud computing after some time. Then you translate the quantum circuit to microwave pulses. This is the one of the challenging thing. And then you will execute on the quantum computer, and then you take the result, measurement result, and then user will understand that what kind of output he has got. So therefore, if you look at the basic design of a quantum computer at present in India, it is a 5th floor building. Okay, bottom ground floor you are feeding the information, and from the 5th floor you are taking the information out. So that is the structure. So slowly with the help of the advent of the technology, we will be bringing this 5th floor into a single floor or in your desktop or laptop. Okay. So whenever we study a quantum computing, basically we require to have a quantum compiler. Okay. So now quantum compiler, there are 3 major functionalities. One is the decomposition, then your optimization, and then mapping. So therefore, if you look at a quantum program, so quantum program should be fed into the quantum compiler, which will be segmented by decomposition, a program that means decompose a program into elementary operations, and then you require the optimization always, because any kind of quantum process is the noisy intermediate scale, that is a NISQ process because error prone, so you have to optimize, and then you require to map what exactly that the problem output is. So that is the basic function of a quantum compiler. Okay. Now, if you look at, so basic architecture I showed you. Now you look at the quantum mechanical concept. In the quantum mechanics, every operators are linear, first of all. And if you look at the dynamical variables are observables, and each observables associate an operator. For example, if you try to measure the momentum of a particle, so momentum is an observable. Okay, so we can measure that. So therefore, in quantum mechanics, this momentum is considered as a momentum operator. And all these operators, whatever we have, angular momentum operator, linear momentum operator, position operator, energy operator, all these operators are linear and they are defined in Hilbert space. Hilbert space is that space which allow you to define any kind of operator in the complex domain. Okay. Then whenever you take to this system, we have a wave particle duality that exists. Wave particle duality is nothing but every particle is represented in its motion as a wave, and the wavelength is given by this equation lambda equal to h by p, where p signifies the linear momentum of the particle. And here another point is that the many of the operators, even though they are linear, but they have to have some interface or they have to have some interaction. This interaction picture is basically called as a commutation. And if you look at the position operator and momentum operator, we have given that the IH cross. That means they do not commute with each other. If the this is a commutator bracket. Commutator bracket means you take if you expand the bracket, it is a xp minus px. X and p all are operators, so that means these operators are represented in the matrix form. So therefore, AB is not equal to BA. That from the matrix definition we know, but here also we say that they are not commuting with each other. That means that I cannot have any device which measures simultaneously position and momentum together. And position operator can be treated as a Px equal to minus IH cross del x. If you look at the Py, Pz, same as del x will be changed by the del y and del z. Okay. So now, with the help of this simple concept, it is understood that the next step is to know that the quantum mechanics further equation, that is called the Schrodinger wave equation. And Schrodinger wave equation is basically simple an energy equation where we know that the kinetic energy plus potential energy all together it will be giving an operator which is called the Hamiltonian operator, which is written by minus h cross square by 2m del 2 psi xt by del x square plus vx by, because the Hamiltonian operator is the minus h cross square by 2m del 2 del x square plus v. Okay, and that it will be translate to the energy operator, which is IH cross del psi del t. Okay, so that means a Schrodinger equation is simply like the Hamiltonian operator if it is defined by h and psi is the wave function, which is the position and time dependent, that equal to energy. So if we solve this equation, I'm not going to solve the equation in detail, but the solution of the equation is nothing but I have shown it here, which is the general form of the wave function, and the solution is a some constant e to the power I kx minus omega t. That means I have a wave, okay, and that wave is propagating in the positive direction of x-axis, and sometimes it can travel to the negative direction of the x-axis also. So therefore, the solution will be changed if I change the potential. It is given an example of the infinite squirrel potential, which is defined here. And if you do that, substituting the potential, if it is 0, if you look at with the boundary of x less than 0 and x greater than equal to L, potential is infinity. So I cannot have any solution with the infinite solution. That is why it's called infinite squirrel potential. But whenever it is 0, so we can submit the Vx value in the Schrodinger equation, and we will get that equation which I have shown it here, and the solution will be then treated as a psi x equal to a sin kx plus b cos x. But still we have not got the solution, because until and unless we got the a and b, we cannot define the solution in a closed complex form. So therefore we require to quantize the whole situation, and here only the quantum mechanics comes into picture. Quantization means that the solution of the wave function will be treated as a quanta. Okay, so therefore the wave function which I have shown it here, if you integrate over the complete domain, you will get that your constant a, and the constant a when you derive, if you submit into the wave function expression psi nx is equal to, you will get that the square root of 2 by L into sine n pi x by L. So the bottom equation is giving you a quantized version of the wave function. And these functions are very much identical to those obtained from a vibrating string. So that means a classical picture where the vibration of a string, when you are doing, it can be quantized by using this expression. So quantized energy, then what will happen? The energy corresponds to Kn equal to n pi by L. So you submit that will be giving the twice m En by h cross square. From there, I can easily calculate the En, that is energy of the nth level. And if you submit the n equal to 0, 1, 2, 3, you can see how the wave function looks like, and what are the quantum energy like E1, 4E1, 9E1. So all these kind of thing will be there. E1 is your energy of the ground state. So therefore, if we change another problem like simple harmonic oscillator, you can see that the potential will be in the simple harmonic oscillator potential is nothing but the half kx square. And if you submit that potential expression into the Schrodinger equation, we will be having this equation like d2 psi dx square into alpha square x square minus beta over psi. And then alpha square beta is already defined. Using that, we will get some solution. And that solution will be equal to that, the psi n equal to hn e to the power minus alpha x square by 2, where hn will be called as a Hermite polynomial. So detailed solution is possible. There are many textbooks where we can see that how the solutions can be taken. But for the quantum computing, this concept is sufficient that if I have a harmonic oscillator potential, what is its solution? Detailed derivation is not required for the quantum computing angle. So again, if we go for the various kind of mode of the parabolic potential well, which is basically half kx square, simple harmonic potential, then you can see that the energy can be mapped into the n plus half h cross omega. So if n equal to 0, then ground state energy is half h cross omega. Classically, there is ground state energy means 0. But quantum mechanically, ground state energy is not 0. It is a half h cross omega. So this is the deviation path from classical to quantum. Okay. So in the quantum mechanics, energy of the ground state is not 0, but in classically, it is 0. So that's the meaning of the introducing the parabolic potential well. Okay. So now we can have the various kind of well, like potential barrier. The left-hand side figure is showing the potential barrier. And if a barrier, if the particle is coming, depending on the height of the barrier or energy, you may have the incident wave, you may have a reflected wave, and you may have a transmission. Okay. So in any kind of optics, you can see that the incident wave is coming, you have a reflection, you have a transmission. So using that, we can have the various kind of region Schrodinger equation with respect to the potential equal to 0, the left-hand side of the barrier, potential equal to V0, that is height of the barrier, and potential is equal to again 0, which is beyond the right-hand side of the. So we have a different solution of the wave function, and as the waves move from left to right, we can simplify the wave function to the as an incident wave, reflected wave, and transmitted wave also. So therefore, once we have both the things, we can expect that the reflection coefficient, which is mentioned here, B star into B divided by A star into A, and then we have a transmission coefficient also, which is again written into F star F divided by A star A. So having this concept, we can apply some definite boundary conditions, and these boundary conditions, it will be treated as a that you know that you can have the transmission probability, which is t equal to 1. Just 1 minute. Huh? So you can have the transmission probability, which is expression here already. And this transmission probability is very, very important from the point of many angle. And as you know that this year Nobel Prize got by the tunneling concept of the quantum dot, and this transmission probability will be giving you the quantum tunneling phenomena. So this is the tunneling. And that means in the tunneling, when tunneling will take place, tunneling will take place only when if the energy of the incident particle is less than the potential height. Okay. So obviously, using this tunneling, we have a lot of devices like tunnel diode or tunnel transistor or many other things can be easily possible to design, where we require again that the tunneling phenomena will be treated as a transmission probability, which is already mentioned there. Okay. So using this concept of the various kinds of potential, user can solve the Schrodinger equation and come back to the concept of the quantum phenomena. Okay. Now we have the Schrodinger and Heisenberg picture. In this case, you can see I have defined here the state vector changes with time, but the operator remains constant with the time is called the Schrodinger picture, whereas the operator changes with time while the state vector remain constant with time is called the Heisenberg picture. So there are two pictures, Schrodinger picture and Heisenberg picture, and any kind of operators, the expectation value is only important from the quantum phenomena. So if you look at the Schrodinger picture, I have a Schrodinger equation already mentioned, IH cross D psi dt equal to H psi. So the solution will be possible to get that very simple. It is ordinary time dependent differential equation. So we can easily get, but having this solution, if you look at the time t equal to 0 to time t equal to t, we can see this particular thing that e to the power minus I h t by h by 2 pi is an operator. So this gives you the idea that quantum mechanically, any phenomena is based on some operator. That means I have a time-dependent state which I will get by operating an operator on the time-dependent state, which is at time equal to 0. So that is the fundamental meaning. So therefore, operators concept is nothing but to transform from one state to another state. Okay. So continuing the Schrodinger state, you can easily see that since it is a, and please remember that all the wave function, whatever we are getting, they are complex in nature. Anything you define in the Hilbert sets, they are always complex in nature. So therefore, corresponding to a vector called the decade vector, you may have the conjugate that is called bra vector. So the solution of the conjugate bra vector is showing here. Okay. So Schrodinger equation, if you consider, you can take the time derivative of an expectation operator and time derivative of the expectation operator. Expectation is nothing but the average value of the operator. You can take the average value of the operator between two states. If the both initial state and final state are same, then we call that the expectation operator, and time evolution can be easily captured by Schrodinger picture. So if you look at the various kind of variation, you can finally see that the expectation value of the any kind of operator is nothing but that operator and Hamiltonian. So commutation of the operator and Hamiltonian. This is the basic important concept of the quantum phenomena. Okay, so that means you understand that whenever we got the expectation operator time derivative, it will be nothing but that operator and Hamiltonian commutator. So that means operator and Hamiltonian, we cannot measure the simultaneously. That is the basic concept of the Schrodinger picture. Whereas in the case of Heisenberg picture, you have the operator e to the power IHP by H cross, which is an unitary operator, and therefore you have the solution of psi H. Heisenberg picture, their state vector and operator file is given here. So the solution is nothing but here. It is a AS, which is operating by the sandwich between the two operators like e to the power IHP by H cross and e to the power minus I. Because in the Schrodinger Heisenberg picture, we have seen that the operators are basically time dependent. Okay. In case of Schrodinger picture, the wave function is a time dependent. So we can easily calculate the operator. This is derivation is not important, but if you wanted to do some kind of research on this, definitely it is from that, since it is a FDP program. So therefore, I thought that it is important for the beginners to understand that what is a Schrodinger picture and what is a Heisenberg picture. Okay. So then you can define, and you can see that in the Heisenberg picture, again that we are getting that similar kind of concept that time evolution of an operator is nothing but the operator and the commutator bracket of the operator and Hamiltonian. Okay. So coming back to the again harmonic oscillator in the another form, it is nothing but that Hamiltonian of a harmonic oscillator is p square by 2m plus half kx square. Obviously that your equation is Schrodinger equation H psi equal to E psi, and we have understood that the momentum and coordinate, they are not commuting with each other. So that is why the commutator bracket is IH cross. So Hamiltonian I can write, if I just mention that the M equal to 1, K equal to 1, H cross equal to 1, I can scale that the Hamiltonian in the form of the half p square plus x square, where I can define one operator like A, which is I by root 2 of p minus ix, called as a annihilation operator, and A plus is 1 by I root 2 p plus ix, which is called the decreation operator. So if I take the product, you will get that the H plus half. So therefore, Hamiltonian can be treated as a half of A plus plus A plus A. So this gives the concept of the if I define later on, you will see that the A and A plus is a creation and annihilation operator. So they are mapping with the photon. So therefore, lot of photons can be placed in one jar, and that gives the a totally different, and this is the concept of the Bose-Einstein condensation. And so therefore we can think about that the photon can be used as a single qubit, and that is why quantum computing starts growing by considering this concept H is equal to half A plus plus A plus A. And later on we will see that this concept of the Hamiltonian definition is nothing but the entanglement of the photons. Okay. So if you have the derivation, you can easily see that creation operator basic concept is that it is creating one state from the n to n plus 1 with a coefficient of square root of n plus 1, whereas annihilation operator, it is downing the one state from n to n minus 1 with a coefficient of square root of n. And if I do that, you will see that the energy is half 3 by 2, 5 by 2, 7 by 2, because we have already seen that the energy is nothing but the n plus. So this again concept that if photon can be considered as a qubit later on, so why electron cannot be considered as a qubit? So this is a new challenge that yes, we can also have a concern that the electron can be considered as a qubit. Okay. And therefore some lot of device can be made. As present, the qubit concept will be based on the photon, but you can design by different operator, or later on we'll see that the operators are nothing but the gates. So these by you can find out that the electrons also can be considered as a qubit. This is the first one circuit which I thought that it is a very important circuit. That means a quantum electronic circuit, how does it look like and why it is linear? We everybody know that the LC circuit is a classical, very established circuit whose frequency is nothing but the 1 by square root of LC. I have given some kind of parameter. Using that, we go for the 5 gigahertz. Now look at just think about the classical oscillator. In the classical oscillator, you have only one frequency. But if I transform this equation or transform this total phenomena in the quantum, you can have the many different energy, like 0, 1, 2, 3, 4. All the different state, and they have a different energy. Having the different energy, the beauty is that if I look at this as a simple coil or bulb, so that bulb is having only one intensity of the light in case of classical. But if I look at from the quantum, the same bulb can be treated as a, if it is a maximum is 100 watt, that can be down to the 60, 50, 20, 30, all this quantum of the intensity in a same bulb we can have. And that's the beauty. And that kind of thing, you can see it is available in the market. So therefore, how does it take place? I have a simple voltage across the oscillator is a V equal to Q by C, which is minus L di dt. So Hamiltonian can be written as a half CV square plus half Li square, because Hamiltonian is nothing but energy. So energy density per unit capacity is nothing but the half CV square, and energy stored in an inductor per unit volume is a half Li square. So you submit that the definition of V and L. So you can see that the half Q square by C plus half phi square by L, where Q equal to Vc and phi equal to Li. Now having this equation, classically if I take the differentiation of the Hamiltonian with respect to Q, I will get that the minus phi dot, and if I take the derivative of the Hamiltonian with respect to the flux, I will get the Q dot. So this gives the classical equation of the Hamiltonian. Okay, that means my charge and flux, they are canonical variables because they constitute the Hamilton's equation. So therefore what happened? I can have a complete circuit, Lagrangian, and I can take the Q I can take the Hamiltonian, and then I can form a Lagrangian equation. So a simple classical electromagnetic circuit can be converted into a quantum electron circuit. Later on, this it will give you the superconducting qubit. That is why this concept is there. So you have the quantum version of the Hamiltonian, and so you know that the canonical variables are charge and flux. So automatically they cannot be measured simultaneously, so they will not commute with each other. Similar to the XP, here it is the IH cross. So the mapping is that the X is nothing but the here flux, and P is nothing but the Q, that is the charge. So therefore XP equal to IH cross. Here also that the X phi and Q as the IH cross. So Hamiltonian you can submit, you will get that. And here you see, as I mentioned, that the H is nothing but the H cross omega A dagger A plus half. So we have a simple parabolic potential, but in the quantum mechanical, this particular circuit is giving you the lot of energy. Okay, because A plus A is nothing but the your N, that is number of operators. Number of operators means number of photons occupied in that particular well. So obviously we can have the raising and lowering operator, and then raising and lowering operator can be mapped into the impedance of the device by this equation 1 by square root of 2 h cross zc and zc, because this is derivation is very simple. So the charge and flux you can measure in terms of the creation of the photon and annihilation of the photon. So obviously then creation, photon can be created, photon can be destroyed. So using that, we can have the charge and photon. So in the quantum mechanically, we describe charge in terms of this expression and flux in terms of this expression. So if you do that, then complete your electrodynamic circuit will be converted into that. একটু পরে কথা বলছি, পরে কথা বলছি. So therefore, we have this concept. This is the fundamental concept of quantum mechanics. Okay. Now, whenever you go for the study of how to implement the quantum mechanics, the first algebraical concept which is required is the tensor product. Okay. Tensor algebra is very, very important, because later on you'll see that whenever we have an operator, then we require to have the tensor concept only. Okay. We can have the 1D, 2D, and 3D operators both. And in the tensor, all the energies E1, E2 with the dimension of N1 and N2, they will be always mentioned as the tensor product. And tensor product is linear. Whole quantum computing is based on three type of product. One is inner product, then outer product, and third one is the tensor product. Okay. Once everybody is knowing at the teaching level what is inner product, outer product, and tensor product, then 50% of the quantum computing is digested by him. Either he is a faculty or he is a participant, a student. Now, if you look at the tensor product notation is like this only, E1 cross E2. Okay. And if you have the vectors belonging to E1 are there, so tensor product I can write phi1 and x2, and then we can write the phi1 and x2. So the tensor product is linear. We can always go for into this kind of concept. Okay. So then we can have the tensor product is distributed. Distribution means any kind of vector calculus we can easily write the tensor product, what is the distributed. So I have shown it here, tensor product is a distributed, and also tensor product of the basis is a basis. Okay. So we can have the many kind of mathematical expression, but need not to worry about that any mathematical expression. In practice, this mathematics will come into a different angle. Okay. So but the tensor product of states I can write. Now one thing which is required to be known, that any kind of state can be expressed as the linear combination of other states. So this linear combination is giving the basis representation of that. So here the ket ui and ket vj, they are basically basis states. So whenever you go for the computation, the entanglement or the tensor product of the basic space are very, very important. Okay. So that's why I shown here this is a tensor product of these two basis pairs. So we can submit, and then you can see that the coefficient ai bj, and then vectors are tensor product basically. So therefore many algebraical procedure we can mention here. We need not to go into the detail, because eigenvalue operation and all these things will come into. But here is the most important, how to take the tensor product of the 2 by 2 matrix. I have shown that the A and B, there are 2 by 2 matrix. If I try to take the tensor product of A, it is nothing but the 1 you will take from the A and complete B you will take. So that's why 1 into 3 is the 3 and 1 into 5 is 5. 3 into 3 is again 9 and 4 into 5. So ultimately what is supposed to be done, your 1 you take and 3, 5, 7, 2. So you get the 3, 5, 7, 2. You take the 2 and 2 into 3 is 6 and 2 into 5 is 10. 3 into 3 is 3 into so this 2 again you go for the 7, 2, so 14 and 4. Similarly for 3 and 4 also. So the tensor product of the each and every element will be interacted with the each and every element of this. And this kind of concept we have got in where? Can you tell? This kind of concept we have got in the neural network. So therefore, tensor product is very, very important to digest the neural network. And we call in the machine learning that the 2 by 2, when you go for is the artificial neural network. If you go for the 3D tensor, we go for the reinforcement neural network. And when you go for the 4-dimension tensor, we call it the convolutional neural network. So that means to get the neural network concept in the quantum computing, the tensor product is very, very important. And right hand side, I've shown you simple a Python code where you can get your tensor product with the 2 by 2 matrix. It can have the 4 by 4 matrix. Now, with the help of the preliminaries, we can easily conceptually take what is a quantum bit. Quantum bit, we already know that the qubit represents a quantum state. Classical computing is based on the simply binary digit called bit, but in the quantum computing, it is based on the quantum bit called as a qubit, and qubit are nothing but the quantum state of the gate 0 and gate 1. Okay, and these are the two unit vectors in a two-dimensional complex vector space. They will constitute the computational basis vector. That means any kind of arbitrary vector we can, or state, we can write in terms of a linear combination of the gate 0 and gate 1. So basically qubit is storing the probability of information, and from this point of the basis vectors, we can form some linear combination of state. So therefore, qubit 0 is represented as a column vector of 1, 0, and qubit 1 is represented as a 0, 1. So we can construct an arbitrary quantum state like gate psi equal to alpha of gate 0 plus beta of gate 1, where alpha and beta are complex number. And so these coefficients represent if you look at the mod of alpha square and mod of beta square, they represent the probability of that quantum state, which is gate psi, in the quantum state of gate 0 is nothing but the alpha square. Similar to the gate psi probability in the 1 state is nothing but the beta square. So they are basically coefficients are giving that the square represented basically they are called as a probability state. So using this, we can make many of the combination. If I have a basis state like say plus and I plus, so here you see that we have taken a linear combination. So basic concept of the quantum computing is that all these qubit 0 and qubit 1, they are always in a superposition state. So that means simultaneously measurement is possible, and that is the powerful of the quantum computing, which is totally different from the classical computing. But whenever we wanted to measure something, so you require to destroy their superposition concept. So measurement is collapsing the superposition of the qubit concept, and otherwise quantum computing will allow you to consider all the qubits in a superposition state. And whenever you have a mixture of these two, so that means they are not pure state, they are the mixed state. So you can have a 2-qubit system. In the 2-qubit system, you can have the qubit 0, 0, qubit 0, 1, 1, 0, 1, 1. And similarly, if I try to construct an arbitrary state with the 2-qubit system, we have the probability is alpha 0 0 square, alpha 0 1 square, alpha 1 0, and alpha 1 1. So therefore, we can easily write that as a linear combination of that. Now the concept is that the density matrix. From the Schrodinger picture or Heisenberg picture, we can easily write that the IH cross del psi del t equal to H of psi. So if the psi is treated as a rho, then I can write that a density matrix is nothing but that. So what is the meaning of that? We find that the density matrix is a commutator bracket of the Hamiltonian and the density operator itself. So that gives us the density matrix is the mixture of the many kind of state. So we can always write that there is the shift operator, and shift operator can be treated as a, I have shown already, e to the power minus I by h cross h of t minus the 0. Whenever you go for that, it is a unitary matrix. So shift operator is basically called as a propagator. So that means you are propagating the whole concept from one qubit to another qubit and one place to another place. And that gives the time evolution of the density matrix. So time evolution of the density matrix can be further treated as a sandwich between the U and U dagger with the time evolution at the T0 state. So now from that we understood that what is quantum entanglement. Quantum entanglement is another heart of the disparity between classical and quantum physics. In the classically, you may not have the quantum entanglement concept, but it is a primary feature of the quantum mechanics not present in the classical mechanics. That's the thing only I mentioned. In the classical mechanics, this concept is not there, but in the quantum mechanics, the entanglement is possible. But what is the entanglement? Entanglement is nothing but whose quantum state cannot be factored as a product of the states of its local constituents. So that means they are not individual particles, but they are an inseparable whole. So whenever the systems are entangled, you cannot separate them. For example, that if I have a sugar solution, I cannot take the separate from the sugar and water. So that means sugar solution is an entanglement state. Any kind of complex phenomena is an entangled. So any kind of chemical reaction where product is there, product is an entanglement state always. Because from the product, we are not in a position to separate the constituents. So therefore, entanglement definition is nothing but it is a pure mixed state where individual constituents cannot be separated. And another advantage of quantum entanglement is that if you try to measure the one, because they are entangled. So if we try to measure one particle which is entangled with other particle property, I need not to measure at all. Measuring one system, we can always get another particle. And this entanglement, since it is not understood by the Einstein also, so he mentioned a phrase that spooky action at a distance. So the entanglement phenomena is an example of the Harry Potter also. Because if you see that if someone has watched the movie properly, you can see that that fellow is here also existing, another also existing. So when you are going for the another, we can say that his soul is existing. So if I measure something, so automatically soul get affected. So that's the meaning of the quantum. So we can say that the quantum entanglement is the phenomenon of a group of particles being generated, interacting or sharing the spatial proximity in such a way that the quantum state of each particle of the group cannot be described independently of the state of others, including when the particles are separated by a larger distance. Okay, so there are many variations of the quantum entanglement is possible, but to be a very concise definition of the quantum entanglement, that the system cannot be separated from the entanglement state. And another point is that if you measure one system, automatically other measurement will come into, because measurement of the other system you are not doing directly, but automatically it will come because they are the tensor. For example, the ear and head both are entangled. Why? Because if you pull the ear, automatically head will come. I am not asking that the head to come, but head and ear, they are entangled. So obviously the definition of the entanglement is like that. If you measure one system, another system measurement also will come into picture. So automation can be done by the entanglement. And if I have the many kind of entanglement, say n number of entanglements. So only one measurement will sufficiently measure the whole system, and that gives the faster computation. So this is the entanglement of two photons, and you see that the way I have written that the A1 and A2 plus B1 and B2 entanglement is only possible mathematically by taking the tensor product of the state. Okay, this is the example of the two photons entangled. So therefore, when you are doing that, ultimately what we are trying to do, it is nothing but the density matrix. So density matrix, why it is important in the quantum computing? Because density matrix is the first example of the quantum entanglement. If you look at the zeta, which is 1 by root 2 0 0 plus 1 by root 2 0 1, then you can see that the zeta can be mentioned as this way. I can form the density matrix by taking the density matrix definition, which is nothing but the tensor product of the both the things, or the outer product also you can say. So the density matrix can be written into this form. This is the normal tensor product, and then density matrix for the various dimension we can. So we can say that this once you have a density matrix, I cannot factorize. So the density matrix are always in the entanglement state. Okay. So then this is an example of the inner product and outer product. I have a two-state phi and psi. If I take that the overlapping, so it is nothing but the gamma star alpha plus delta star beta depending on the definition. So this is called as the overlapping of the two states is basically a inner product. Whereas if I take the outer product, I can have this expression ket psi and bra phi, so which is given. So outer product is basically the multiplication of the both the states into this form, and it is not the overlapping. Okay. Whereas in case of the tensor product, you can see that when you go for the action of an operator on a quantum state, so this is an operator. Operator is remaining that the dynamical variables are observables and observables are operators. In the operators are nothing but the matrix. Okay. So therefore this operator A is taking as a matrix, which can be written into this form, and then we can, if I operate this matrix by the another vector, say phi state, we can always get the expression. Okay. So therefore, what is the action of an operator in a quantum state? It will operate on the quantum state and transform into the another state. So then now here the definition that the operators in the quantum computing is a quantum gate. Okay. These quantum gates are similar to the classical gates, but they have to be reversible. Reversible in the sense that from the output you can come back to the input. That's the meaning. So you can have a quantum gate, a single qubit, two qubit, multi-qubit, and as I mentioned here, the dynamical variables are observables. Observables associate operators. Operators are represented in the form of matrix. Quantum gates are represented in the matrix form. Hence, quantum gates can be treated as an operator. Okay. So meaning of the reversibility is nothing but that as I mentioned that from output you will get back to the input. That is the reverse. So if you try to design a quantum gate, you have to mention that, you have to look at that is reversible or not. If it is not reversible, then it is not a quantum gate. Okay. Physical reversal is a process that you dissipate no energy to the heat. So therefore, in the quantum computing, even though we call that a lot of circuits will be there, but not that much of heat dissipation will be there. And that's the advantage of quantum computing. So this is an example of the various kind of quantum gate. One qubit, I have a gate is nothing but a matrix. If I operate the one input system as a gate state, I will get the another one. So that's the meaning of the gate. So gate is basically transforming from one system to another system. So you can have a single qubit gate like Pauli X gate, Pauli Y gate, Pauli Z gate, and if you look at the Pauli X gate, its matrix information can be mentioned in the top right corner. That is a summation of the input and output. And if I look at X matrix can be written as a qubit 0 and qubit 1 plus qubit 1 and plus qubit 0. And if you operate that, you will see that the Pauli X gate representation is nothing but a simple classical NOT gate. That means qubit 0 is transformed to qubit 1 and qubit 1 is transformed to qubit 0. So therefore, it is a NOT gate. So Pauli X gate is a NOT gate, Pauli Y gate is a complex shifting, and Pauli Z gate is a flip gate. So Pauli Y gate also you can see that the qubit 0 is transformed to I1, means I qubit 1, and qubit 1 is transformed to minus I qubit 0. Matrix representation is shown here. So Pauli Z gate is a flip gate, and you can have a phase gate, pi by 8 gate, various kind of gates we are there. So all the quantum gates are nothing but the maybe single qubit, maybe 2 qubit, maybe 3 qubit. So these are single qubit gate. So we can have the Pauli X gate matrix represents 0 and 1 0. Pauli Y get 0 minus Y I 0. And Pauli Z gate is 1 0 0 minus 1. So X gate is what? X gate is a NOT gate. Z gate leaves that the qubit 0 remains unchanged and flips the sign of qubit 1. I have shown that the mathematics that the Z psi is operating on that. Okay. So therefore, we understood that the Pauli spin operator gives the quantum gate, that is the X, Y, and Z gate. Now, from that angle, we can see the Hadamard gate. Hadamard gate is represented to this form 1 by root 2, 1, 1, 1 minus 1. So any state like alpha 0 plus beta 1, if you open the Hadamard gate, then you will get the output like alpha 0 plus 1 by root 2 plus beta 0 minus 1 by root 2. It's very simple. You can operate the matrix. Now, once we have the right hand side, so that means Hadamard gate function is to prepare an entanglement state, because the right hand side state is basically entangled state. So the job of the Hadamard gate is to prepare an entangled state or mixed state. So now if you look at it acts on a single gate, it gives the superpopulation of both the gate. So another advantage of the another gate, if you look at the H dagger H, that means complex conjugate at transpose and multiplied by H, it will be always I. All maximum quantum gates follow the same principle, which will give the no classical equivalent. So if you prepare to develop the entanglement, Hadamard gate is the most important. So these are matrix form I have shown you there, how Hadamard gate can be taken, and why the Hadamard gate is matrix form is 1 by root 2, 1, 1, 1 minus 1. This derivation it will show you that the Hadamard matrix form. Amazing part is that H square will be equal to I and H inverse equal to H. So this is the amazing situation of the Hadamard gate. Maximum concept of the quantum gate can be obtained by the Hadamard gate only because of this property that H square equal to I and H inverse equal to H. So if you sandwich both the systems by a Hadamard gate, so for example, the Z is written in the matrix form as the 1, 0, 1 minus 1. So if I sandwich the phase gate 1, 0, 0 I, like that the SX S dagger, that I will get the Y. So this gives the concept that the sandwiching of the gate is possible, and if you do the sandwiching between the two systems, I will get the another gate concept. So this is the idea of the how to prepare a circuit. You can have a which is not possible at all in a classical computing, square root of 1 qubit gate, and to get the square root of gate, the derivation is not that important. You can see that the square root of x is possible, which is 1 by root 2 I of I1 1 minus I. The derivation will come from the de Moivre's theorem of the complex algebra, and root y is given into this form, root z is given into this form, root h. That means square root of quantum gate is possible, whereas square root of classical gate is not possible. That is the difference again between classical computing and quantum computing. So as I mentioned that if I sandwich your Pauli Z gate between two Hadamard gate, I will get the X gate. Similarly, if I get further the H square root of ZH, I will get the square root of H. So therefore, from this derivation, we can get what should be the matrix representation of the square root of Pauli gate. So anyway, you can get further the matrix formulation of controlled Z gate and controlled H gate. So many of the control gate we can prepare from this here. You can have a more single qubit depending on your play around with the matrix. and then you have a pi by 8 gate. These are all single qubit gate. Then having this, we can also have a various kind of rotation operator, that is Rx theta, Ry theta, Rz. They are also considering as a quantum gate. And various representation of the quantum gate will be there. Then you can see that how a simple number can be computed in the quantum computer. This is the least significant bit. I have a bit string. I can always go for the QN1 and this one. So ultimately, idea is that a decimal number you represented by a binary representation, and whatever the 0-1 sequence should be get, that itself it will be a quantum gate. And that is the meaning of this particular slide. So we have a control NOT gate. In the control NOT gate, the basic the control, you have a control bit, you have a target qubit. Control bit remains same, but target qubit is split. So therefore, control dot matrix representation I have shown here, and I have shown it here, and this control NOT is nothing but the equivalent of the XOR operation. So whenever a logical operation XOR takes place, so we require to use the control NOT gate. It is a 2 qubit gate, remember. So control bit will be remain unchanged, but control target bit will be changed. How that the target will change? If you look at the truth table, you can see that the ket 00 will be equal to ket 00, because control bit is here 0, so it will be changed, not changed. But 01, it will be again 0, because control qubit is 0, so it will be remain as 0, so automatically target qubit will not do anything. But if the control qubit is 1, it will be always 1, 0. Why? Because 1 plus 0, it will be 1. Similarly, 1, 1, it will be 1, 0. So that means in this case, the control qubit will remain same, but target qubit will be the sum of the control qubit and this one. And this way, we can get the matrix representation of the control gate, C0 gate. And matrix representation is same that way. I have shown that it is an XOR operation. So target qubit will be that your control qubit plus XOR of the target. Okay. So therefore, we can have the matrix representation, and ultimately you have the 1, 0, 0, 1 and 0, 1, 1, 0. So this matrix representation of a gate is very, very important. Same way we can proceed to the algebraically. X will be remain as X, Y will be X or Y. So C0 can be mapped into this form, that C0 XY, it will be X and X or Y. You can have a multiple qubits, and when you have a multiple qubits, you can have the NAND gate, NOR gate, many of the other gate we can prepare. So all these quantum versus classical gates we can compare from here. Then we can have a swap gate. In the swap gate is again 2 qubit gate. What happened? A will be B and B will be A. And matrix representation can be formulated by using the same principle of the summation of the input I and output I. You can have a 3 qubit gate, that is called Toffoli gate. And Toffoli gate, here you see, I have shown the matrix representation. In the Toffoli gate, what happens is a 3 qubit, 2 control bits. So A will remain as A prime, B will remain as B prime, but C will be changed to the C plus XOR of the both the operation, that the A and B. So that is why control Toffoli gate is a 3 qubit gate, and many of the magnetic phenomena can be understood by the Toffoli gate. So these are matrix representation of this. Ultimately, area now you are seeing that the quantum computer is based on simply linear algebra or matrix algebra. Okay. So then this is the transformation one can design. This is called Walsh-Hadamard transformation, where you require to do that. If I multiply the Hadamard gate n times, what I will get? The expression is written here, 1 by square root of 2 to the power n, summation of x equal to 0 to the power n minus 1 and x. Okay. So we have a classical and quantum system. This is the probability state, and this is the quantum state. Okay. So quantum computing is always in probabilistic in nature. So that's why the probability of a quantum state can be possible by taking the square of the coefficient. This is a 1 qubit gate, and when you have a gate, now the question is that can you have a series and parallel combination of quantum gates? Yes, it is possible. Series combination, this is a very good research domain, series and parallel combination of quantum gates. So whole of your electrical circuit can be transformed to the quantum gate, like Thevenin's theorem, Norton's theorem, pi gate, T gate, all the circuit, pi filter, T filter can be transformed into the quantum gate. Series combination is nothing but the when gates are applied in series, they are executed one after another on the same qubit, and you get the A star B as a matrix representation. Whereas in a parallel combination, you have the tensor product. So these are the different. Series combination, you have a simple inner product, A star B, or matrix product, but in the parallel combination, you have a tensor product. How does it look like? It looks like that. A1 and A2, we are connecting to the series. So I take that from right hand side to left hand side. So A2, A1 will be my scalar product. That is the inner product. But when you go for the parallel part, it is nothing but the tensor product of A and B. Okay. So in the many combination you can have, series you remember is inner product, but parallel is nothing but the tensor product. And tensor product I already shown. So if I have a parallel Hadamard gate, I can take the tensor product to get the basic output. C0 is a 2 qubit gate, as I mentioned. Since the 2 qubit, it is always taking as a tensor product of the things. Now Hadamard gate, it is a beam splitter. So that means this is the yellow sign is a beam splitter. You are putting the qubit 0, and reflecting part is the qubit 0 again, and but the transmission part is a qubit 1. So that is the Walsh-Hadamard transformation will give you the concept of the beam splitter. That means Hadamard gate is splitting the whole beam to take the qubit 0 and qubit 1. So this is a matrix representation of the qubit 0 and qubit 1. And then we go for the 2 qubit gates, 2 input qubit gates, 2 qubit gates, many kind of combination. I am just showing because the algebra is very simple. Okay, now if you look at the Hadamard gate, I am putting in the series. In this case, what happened? Both the Hadamard gate matrix representation, I have to take the inner product, and then only I will get the complete outcome. But if it is a parallel, then I have to take the tensor product of that. So these are 2 qubit gate. These are 2 qubit different gate we can have. We can have the many of the 2 qubit gate, and you can see that both the Hadamard gates are in parallel. So I have the outcome get shy, and then we can have all the matrix represented the tensor product form. Okay. Then series combination of Hadamard gate is nothing but that the H and X, they are the Hadamard gate, and then so therefore what happens when you go for this one, you will get a combination of Hadamard gate and this one. So we can have the XH, you can have the HX, but whereas in the parallel combination, you will see that both the Hadamard gates are parallel, so we have to take the tensor product. These two only points to be remembered. Series combination of gate is nothing but the inner product, but parallel combination is nothing but the tensor product. So we can have the various combination of parallel combination. You can check that the commutation, because gates are operators, so whether they are commutation not there. Commutation means whether gates are possible to measure simultaneously or not. Okay, so this is a control you get. You can have the control you get into this form. You can have a control not gate as I shown here, and then we have another 3 qubit gate which is called Fredkin gate. In the Fredkin gate, we have a P equal to A, outcome P equal to A. The second control bit is the Q equal to AB and XOR of the AC, whereas third one will give the AC and AB, okay, with an XOR operation. So if you take it the matrix representation, so Fredkin gate is the maximum. And this Fredkin gate and Toffoli gate are very important gate for the combination of a quantum circuit. So these are XOR gate we have mentioned in algebra. This is the AND gate. So that means all your logical Boolean algebra can be possible to devise by using the quantum gate. This is the OR gate. Okay. And these are the various combination of the gate can be done by this one. So somebody can work with the quantum gate as a research component. We can have a no cloning theorem. This is very important theorem, because here this is the unknown quantum system cannot be cloned by unitary transformation. So you cannot copy the system from one system to another system. That's the meaning of the no cloning theorem. Proof is I have given for teaching only, but of course here you can skip this one. So in general, a qubit system, how the gates act on a qubit, in general, you can see that you have a phase shift gate where you are operating the e to the power ix5, Hadamard gates, NOT gates, and control NOT gate, swap gate, Fredkin topology. So this structure is sufficient, and whenever the two qubit state, you can have a tensor product of the both the qubits. You can have the universal quantum gates. So that means universal quantum gates, by defining the manipulation of the qubit, I can go for the C naught, I can go for the phase gate. So one gate is sufficient for knowing that the universal quantum gate. There are some theorem, so that if everybody works on the quantum gate, this you have to go through all the universal quantum gate. Theorem says that the set of single qubit gates and C0 gates are universal. That means any unitary gate acting on an n qubit register that can be implemented with a single qubit gates and C0 gate. And this is the meaning of a universal gate. And whenever a universal gate, only that the last part of the gate will be reflected, which is shown here, U equal to AC and BD, which is also unitary. And if you see that whenever unitary gate will be operated on a vector, you have only the first part alpha plus beta C and bottom part alpha B plus beta D. Remaining all things all will be equal to 0. So this is a kind of various algebra can be done by lemma. I am skipping that because this now it is a important unitary transformation. Unitary transformation, a qubit state evolves under the action of 2 by 2 matrix according to this concept. Okay, so therefore, as I mentioned in the first time, the Hamiltonian is a photonic entanglement. It exactly this one, and this by photonic entanglement, you will get that the complete beam like A dagger B plus B dagger A. Okay, so this kind of beam is very important, and this is only possible to get the some kind of pumping phenomena. Okay, so these are the separable state, these are the entanglement. So entanglement state are not the separate state. So okay, it is a non-local bipartite superposition state. Then using that you require now all the gates when you are arranging a particular sequence phenomena following some algorithm, we have a quantum circuit. So quantum circuit is nothing but a sequential combination of quantum gates following some algorithms. So algorithms are nothing but the basic state by which we are trying to design some kind of problem. Okay, if you look that you have a quantum parallelism and entanglement capability, and using that we have a various kind of algorithm like quantum Fourier transformation, quantum phase transformation, HHL algorithm, factoring algorithm like Peter Shor's algorithm, Glover's algorithm, which is a search algorithm, quantum Hawk search algorithm, Simon's algorithm, and there are many kind of algorithms. So one can always start with the one algorithm, not all that things together. So anyway, this is a algorithms are nothing but the discrete integral transformation, where a discrete integral transformation is nothing but the you are defining a kernel, and that kernel you are operating on some function which is given, and you know that it is a quantum Fourier transformation. Quantum Fourier transformation, we have a Fourier kernel, we have a state which is giving that the coordinate state to momentum state. That's the meaning of the quantum Fourier transformation. So this is the idea that the f bar tilde equal to k into f. So then you have a quantum integral transformation, QIT. Then, as I mentioned, that the quantum Fourier transformation is a crucial operation in the quantum computation, and Qiskit is a quantum software tool people can use to understand the whole phenomena. Okay, so this is the understanding that the QFT is nothing but the transformation. Analogy to the discrete Fourier transformation, it has got very efficiency, and it has to be done always by Hadamard gate. So if you look at simple, I have a transformation that the yk equal to 1 by root 10, and this transformation, it will give me the quantum Fourier transformation into this part. Okay, so mathematical background is that I have a state yk, which is done by the kernel e to the power 2 pi ijk by n, operating on the xj state, so that j can be mapped to the k state by using the quantum Fourier transformation. And quantum Fourier transformation is always a unitary transformation, where you will get the frequency 1 by root n and all these things together. So there are the mathematical background. I am not going the detail because, but an example you can see. You can see that the example psi equal to alpha 0 plus beta 1. In this case, n equal to 2 because x0 is your alpha and x1 is the beta, that is the coefficient. So we can always prepare the y0 by using that formulation, which is 1 by root 2 alpha plus beta. Y1 is equal to 1 by root 2 alpha minus beta. So unitary transformation of the quantum Fourier transformation we can write into this form: 1 by root 2 alpha plus beta operating on qubit 0 plus 1 by root 2 alpha minus beta operating on qubit 1. You can have a 2-qubit system. Obviously, one can take the patience and doing all the algebra. Finally, you will get the frequency operation because Fourier transform. Why you do? We do the Fourier transformation from time part to frequency part. Here also same thing happened in the quantum Fourier transformation. Time domain we are shifting to the frequency domain, and that frequency is given into this matrix 1 by 2 and this 4 by 4 matrix. Okay. So 1-qubit system you can design by Hadamard gate. You can have you can write a very simple computer program by using Qiskit to get the Q0 and Q1 and Q2 for a quantum Fourier transformation. This is the simple snippet of the qubit, how we can implement the quantum circuit by using quantum Fourier transformation. So this is the basic phenomena. From the Qiskit, you have to import quantum circuit, provided that the Qiskit tool should be installed at your system. Okay. You can also have an inverse quantum Fourier transformation. In the inverse, from the frequency, you are getting the time. That's the meaning of the inverse Fourier transformation. And these are the inverse Fourier transformation. Some of the examples from the 1, 0 to 2. Then why we need that? We need the quantum phase estimation. This is a quantum algorithm which will estimate the phase of a unitary operator and quantum phase estimation of the 2 sets of qubits. So Fourier transformation is required for doing the quantum phase estimation. How does quantum phase estimation work? Step 1 is that you put the counting the qubits into superposition, and in the step 2 you apply the unitary operators to the second state. In the step 3 you apply an inverse QFT, and in the step 4 you measure the counting qubits. The last step is always the measurement of the quantum qubit, and this is the mathematical part. Please do not worry about that. Automatically it will be done. Okay, because you need to do the quantum computing. So quantum circuit will be there for phase estimation. These are the various mode of operation. Quantum phase estimation algorithm, as I mentioned, that the initial state create superposition, apply black box, result of the black box, and measure them. First go, definitely it will be very hard, but if you practice, it will not that tough. Then you have a various important part is the variational quantum principle. The variational quantum principle is segmented into variational quantum eigensolver, which will be required to develop some kind of Ax is equal to B program. Okay. So for example, I am doing the variational quantum regression y equal to x plus b by using the quantum computing. Okay. I have a data. In this case of the quantum computing, this is very interesting that in the quantum computer feeding the parameter, and then you, with the help of some cost function, you are taking to the classical computer, you are measuring the theta. If it is not the tolerance, if the cost is less than the tolerance, then you are taking the output. But if it is not, then you are feeding back to the quantum computer. So it is an iterative process to get the estimation of the parameter theta. So you can transform to the whole domain that y equal to mx plus c into the quantum computing, and we get that y in terms of the quantum state. Cost function can be defined into this form, and when you have a cost function, we can take the inner product on a quantum computer, and to get get phi, and the probability measure can be easily done by using that. So this is the quantum order finding. Another how many quantum order finding algorithm is nothing but what is the order of that function, which is showing here the quantum order finding. Algorithm is nothing but you have an initial state, you create the superposition, you apply the unitary operator, and you apply the inverse Fourier transformation to get what is the R. R is nothing but your order of the function. Okay. Then you can apply the Ax equal to B type of phenomena, which is already there in many of the classical thing. But in the quantum computing, we apply the HHL algorithm for solving the large linear system. And this is very important for considering the quantum computing as a quantum data science, because many of the data science program can be treated into AX equal to B. And if this algorithm works, then definitely I can have a quantum data science, or we can have a quantum finite element method. We can have a quantum CFD problem. Okay. So the whole classical part, we are jumping into the quantum by using this kind of algorithm. Okay. Algorithm is said that I have a Hermitian matrix, and where the goal is to prepare the state vector x, which is x equal to b. Then I have a since the Hermitian, I can apply the lot of eigenvector concept. WhatsApp video. No, এটা ধরো তো রিমি এই তো So we can apply the HHL algorithm. We prepare the quantum state. You have the eigenvalue equation, make the new qubit, you uncompute, and then you amplify. So example wise, if you see, I have a matrix A, I have a vector B, and I wanted to solve x1 and x2. So I can write that the x1 minus x3 by x2 by 3 equal to 1, x1 by 3 plus x2 equal to 0. Now using the quantum computing, I can take that the A as a this form, and I can take that the invertible of state. So finally, my job is to calculate that the x, which is A inverse of qubit state B, then I can submit into this form, and using this, we can get the all the algorithm. And I applied this problem into a heat conduction equation, simple steady state heat conduction equation. We transform this discretize into this domain, and we solve this equation by discretize of the whole thing, theta I minus 1. And this concept, if we try to go for your quantum computing, we get that all the in the quantum computing solutions are nothing but the vector form. So naive raw solution vector, tri-diagonal raw solution vector, all these things we are getting. So we get the phenomena, and you can see that a temperature profile for classical, temperature profile while quantum FDM is same, but quantum FDM concept is very computation speed is very high. So therefore we can always apply the quantum computation compared to the classical domain. So this is the result for the HHL algorithm. We can define, then we can go for the Grover's algorithm, which is a search algorithm. If you require to search a large database, which is very complex and entangled, then Grover's algorithm will be worked from here. Okay. So this is a good state and bad state we can always prepare. And with that help of that, of course, I have not considered the many of the algorithms, but these are the basic important algorithm: quantum Fourier transformation, HHL algorithm, order finding, and the Grover search or Petersfield algorithm. And with the help of that, I conclude my session here. So I think that I have completed my, of course, I took a lot of time, a little bit of time I took. I think now, if there is any questions, I can answer that questions. No problem. So I can answer the question. Participants or any other faculties, if you have a question, you can raise that question too.
Participants, before you ask your question, please tell your name also.
So anybody can ask the question, because this is the beginning, I understand. And but since it is a faculty development program, so interaction is the most important. Of course, I believe that in one session everything cannot be done, but you can, because a novice always can ask any kind of question because there is no boundary.
Sir, sir, my name is Shardul Vadalkar. Can you hear me? And sir, I am a lecturer from Gujarat, and I was just curious about how spintronics is important in understanding quantum computing.
Okay. So the first of all, I tell you that your question is very relevant and a good question. Spintronics, as I mentioned at the very beginning of the slide, spin of the electron will give you the electron, whether it is a upscale or downscale, up spin or down spin, right? Because electron has a spin plus half and minus half. They are all the fermions. So spintronics is a subject where the electronics concept is based on the spin of the electron, right? So in the
Yes.
quantum computing, the qubits 0 and qubit 1, they are also giving the phenomena of the up and down. So therefore spintronics, that means electrons are framed in terms of the Pauli gate, Pauli XYZ gate, by using the quantum. So spintronics, if you look at whole branch of the spintronics, is based on the electron spin, and they are framed as a quantum gate by using the Pauli XYZ gate. And that way spintronics transform to the quantum computing. Am I clear to you? No?
Yes, sir. Thank you.
Okay, welcome. Any other questions from the participants? Because more and more questions, more and more interaction, and then program is always success.
If there are no further questions, we can again turn on our cameras for the last group photo for the session 1. So again, I request all the participants if they can turn on their cameras for 2 minutes so that we can have a group photo again. Sir, can you turn off the screen sharing?
Oh, okay. I will turn on the screen sharing. Okay.
Sir, what are the extraordinary features of quantum gates compared to basic gates?
Okay, extraordinary features are that, again, I will say this is a very good question. Extraordinary in the classical gate, you cannot, look at the series combination and parallel combination, right? The first extraordinary feature is that for a quantum gate, from the output, you can come back to the input. But in a classical, from the output, you cannot come to the input, right? This is the first difference. Second difference is that I can have a series combination and parallel combination. So when you have a parallel combination, it is an entanglement. So that means a very few measurement will be sufficient to measure the whole system at all. So that is the great advantage of the quantum gates, which is not possible in a classical at all, because there is no concept of the entanglement concept in the classical gate. So these are the main difference between the two features. You can do the work with the Thevenin's theorem and Norton's theorem, and you see that in classically to break a circuit in a lot of time takes, but in a quantum I do not need. I can take the only a single measurement. It will give me the many other results. Many of the current and voltage diagram, it will be possible by using the quantum gate.
Sir, since you are a physics person, I was just curious that sir, means what kind of materials are useful? The people are researching about lot about topological insulators and Rashba semiconductors, but
Okay.
traditional semiconductors are also effective or not? They.
So in this case, I will tell that when we talk about the material, that is a quantum material or quantum sensors, so
Yes.
the most important part is the nanotechnological material. Okay.
Sir.
So all the nanotechnological material will be useful for a quantum sensor. You can measure the temperature, very, very low temperature you can measure, which is not possible by classical at all. So that kind of thing will be possible. And
That means
nanotechnology material, for example, the 1D, 2D, 3D, you can have a graphene, you can have a dichalcogenide crystal.
like
So all
quantum
these
dots.
quantum dots you can prepare.
Okay, thank you, sir.
Okay, welcome.
The quantum gates are available in market.
Quantum gates are as such not available, but one can design, because you have a availability of the Pauli gate, Pauli Y gate, So by using that, you can devise your quantum gate. There are some nowadays there is a availability of the your what we call the like a microprocessor, some kind of breadboard is available. So you can design the quantum gate by using those breadboard for teaching purpose. Okay, they are available, but slightly costly. You know, it is based on the photon qubit. It is a costly and you require a good temperature. Otherwise, qubits will be collapsed. If qubits are collapsed, then you cannot have a quantum computing. Okay, that's the basic idea.
Okay, sir. Thank you, sir.
Okay, okay, welcome, madam.
Any other queries from the participants?
Shraddha madam, sorry, Bharti madam.
Yes, sir.
If there are no further queries, you can conclude the session.
Yes, sir. Yes. So since we have no further queries, we'll conclude the first session. Thank you, sir, for sharing your incredible knowledge regarding this particular topic. And in spite of your very busy schedule, you have given us your valuable time. Thank you so much. And we are all honored here. And it was a pleasure having you on this particular platform. Thank you very much.
Welcome, madam. Welcome.
The next session will start at 8 o'clock. So participants just wait for the next session to start.
Hope I have considered the within that time only.
Yes, sir. Yes, sir.
Okay. Okay.
It was nice,
Thank
sir.
you,
You have
madam.
done concluded very nicely in time.
Okay. Thank you, madam. Thank you.
Yes, sir.
So I am leaving the session now. Okay.
Yes, sir. Thank you so much.
Okay. Welcome, madam.
Dr. Naresh.
Hello. Yes.
Hello, sir. Yeah. So we will start in just 2 minutes now.
Okay, fine.
Yeah.
Participants, the feedback link is available. Kindly fill the feedback after every session.
Bharti ma'am, we can start the session now.
Dr. Naresh, sir, can we start now?
Yes, we can start, ma'am.
Yes, okay. So for the next session is uh, uh, will be given by Dr. Naresh Raghava, a senior project engineer at CDAC Bangalore, and he has an extensive experience in quantum algorithm design, quantum classical hybrid systems, and quantum communication. He has led multiple projects in quantum algorithms and quantum simulation frameworks. And also, he has delivered invited talks and tutorials in all these areas. So, his current work focuses on developing scalable quantum application modules using Quineus platform and quantum algorithm development. So, over to Dr. Naresh sir for the session. Welcome, sir.
Thank you, ma'am. Thank you for the introduction. So I'm Naresh Raghava. So today, what I'm going to do is that today I'm going to introduce a certain tool called Quniverse. So all of you are attending this particular ATAL FTP on quantum intelligence. So to work on quantum computing, you require certain tools, right? So in this particular talk, what I will do is that I will actually introduce a particular tool called Quniverse, so which will be helpful for you to work on quantum intelligence. Okay, so I will share my screen. I hope the screen is visible. Can you
Yes,
just
sir. Yes, sir.
yes? Okay,
Great,
thank
sir.
you. Yes, sir. Thank you. This tool is called, yes, thank you. This tool is called Quniverse, which will be helpful for the faculty, researchers, and students for modeling, simulation, and execution of quantum and classical workflows. Okay. So, yes. So, in the last session, you actually heard about the basics of quantum computing, right? So, by this time, you are already aware of why do we require a quantum computing, right? So, you're all looking into quantum artificial intelligence. So to summarize once again, so why do you require a quantum computing? Okay, so the screen here, you can actually see the HPC resources which are there in CDAC Bangalore. CDAC Bangalore has this Param Utkarsh high performance computers. Okay, now so these works at teraflops. Okay, very soon we are getting the petaflop systems in CDAC Bangalore. Okay, now so these are useful for weather forecasting, for modeling, and other kind of intensive complex problems. But still, people are talking about quantum computing. So what is why? So where does this quantum computing will help us? Which high performance computers can't solve the problems? Okay. Um, so to just throw a light on it, even you see, even if you have a wonderful quantum computers, so people can't actually just discard the classical computers. Now, what I mean by classical computers, I want to just differentiate the computing which we are already familiar. Let us call it as a classical computing. Okay, and the computing which uses the quantum mechanical principles, we call it as a quantum computing. Okay, now quantum computing can actually solve certain complex problems where high performance computing, they may find it a bit difficult. Say, for example, when I say difficult, see, for example, let us take an RSA security. Okay. Now, if you want to break an RSA secure code, say, for example, you have more than 128 bit, so more than that, right? It is actually challenging for the classical computers to actually, it takes certain time to break the RSA code. But let us look at quantum computing. So quantum computing has certain, so there is a certain algorithm called Shor's algorithm, which uses the quantum mechanical principles for doing the quantum computing problems. Okay, this actually is exponentially faster compared to the any of the classical algorithms. Okay, now that is where quantum computing can actually has an advantage over the classical problems. Sorry, classical computers. Okay. Now, this is one of the example. Okay. Now, to again just go one step back. Okay. Quantum computers will not replace classical computers. Okay. Quantum computers are very specific to certain problems. So in this case, which I referred is RSA security. Okay. Here, classical computers, sorry, quantum computers have an advantage. Right. But you see, many of the problems, still quantum computers may not have an advantage. So it is problem-based thing. So see the now general perception. Now people have actually come to a conclusion that you see, we require both classical computers and quantum computers also will help in actually solving certain problems. Okay. Now this is where quantum computing will help us. Say, for example, let us take this particular problem like in drug discovery or material science. As I mentioned to you, quantum computing, basically the computing way which uses the quantum mechanical principles like a superposition or in quantum entanglement. I hope the previous speaker has actually introduced these topics to you. Okay. And anyway, you will hear more on these topics in subsequent sessions. Okay. So these are certain properties. These are the fundamental principles of quantum computing called quantum superposition and quantum entanglement. So these are certain properties which will help in drug discovery in a faster way compared to the our classical resources. Okay. Now, why is that? See, the reason here is that, say, let us look at this drug discovery. When we're talking about the drug discovery, we're talking about the molecules. So molecules are inherently obey the quantum mechanical principles. So there, quantum computing will have an advantage compared to the classical resources. Okay. So that is where we have to think, like where can actually quantum computing will have an advantage. So when you're talking about AI, so artificial intelligence is actually it is grounded on robust mathematics, right? You have a proper machine learning techniques. So these are extensive mathematical modelings, right? Now we have to see where actually quantum computing will give an advantage. Okay. Now, this is drug discovery and material science, as I told you. These are mainly on because these quantum particles obey quantum mechanical principles where quantum computing will solve the problems in a faster way. But let us look at the other things like an optimization and financial modeling. Here, right, these are nothing to do with this. These are not quantum particles which obeys the quantum mechanical principles. But still, people see that quantum computing will have an advantage in certain problems compared to the classical problems. Say, for example, what it can do is that whenever you have some problem, you need to convert into cubo-based problems. Okay. So once you have the cubo-based problems, actually quantum computing can help in solving these kind of problems. Okay. Now, this is where again quantum computing may have an advantage. Okay. So what is the underlying conclusion of this particular why quantum computing is required? Thing is that we have to select the problems where quantum computing can actually show an advantage over the classical problems. So that is the underlying takeaway. Okay, so we can't just apply wherever quantum computing see each and every problem. So that may actually drain out our resources. Okay, that may not be efficient. So after attending these FTP sessions, I hope that all of you can actually see that what kind of problems actually quantum computing can give an advantage. Okay, that people should look into that. Okay. Okay. Now, after the my brief introduction to why quantum computing and where quantum computing can help us, so let us look at the tools where people like you actually want to develop your own algorithms and applications. Right. Now, there are certain bottlenecks when we're actually trying to work on these things. For example, one is learning mathematics or learning quantum computing. Okay. So there are certain other bottlenecks. See, for example, we have a fragmented ecosystems. So what I mean by fragmented ecosystems, you see, if you have certain algorithm or an application, say on quantum AI. Now there are on the hardware side, right? Quantum computers. So there are various quantum computers are available in the market. See, so there is no one unique hardware. See, for example, IBM uses the superconducting based quantum computing. Okay, Google uses the superconducting based quantum computing, whereas Microsoft they are working on topological based quantum computing. So there is a Xanadu which works on photonic based quantum computing. So even in CDAC, we are actually as of now we are working on two things: superconducting based quantum computing and photonic based quantum computing. Right now, people like you who are started to working are already working in quantum computing. Which kind of qubit technology you want to start with? Right now, that's the one challenge. Like you see, sorry, any question? Okay, fine. You see, that is one of the challenge. Like which hardware we need to start with. Now, whether my application or algorithm will work on this particular hardware or it will give benefit in other hardware. Now, these are certain things people are actually still need to think on. Okay, that is one of the challenges people generally face. The other challenge is that, you see, as I told you, there are multiple hardwares are there. Now there is no standardization. Say, for example, IBM qubit architecture, people try to use Qiskit. People use Qiskit to access their hardware. So Google has their own version called a Circ. Okay. Similarly, people with like Rigetti computers, quantum computers, they have PyQL. So you see, for each and every accessing each and hardware, you need to write. You have to write your own codes in different QSTKs, quantum software development kits. Right now, that's then challenging. People actually face it. Okay. Then other one is the lack of interoperability. See, for example, as I told you now in the earlier slide, some part could be work on classical computers better, and some part work better on the quantum computer. So we need to have this kind of a workflow. Okay. Now that is one of the challenge people generally face it. So this is a hybrid workflow where you have a classical thing and a quantum computers. Okay. And so you're attending this particular session, you see that there are challenges in learning itself. Say, for example, when you're starting with artificial intelligence, maybe many of you are already familiar with that. So one thing is learning about artificial intelligence, then understanding quantum artificial intelligence. Okay, so that means that do I need to study mathematics? Do I need to study physics? Do I need to study computer science? So you see, there is a lot of things we need to segregate properly and we need to learn. So there's a steep learning curve people generally face. Like how do we start working on the problems? Okay. So these are certain issues people generally face. So before we launch our Quniverse, we actually in the LinkedIn, we actually posted certain questions to our you see who attended our webinar series or other FTP programs. Now, one of the thing is that people actually we ask these questions. What is actually see for example, what kind of quantum computing frameworks are you familiar with? So the sample is around 250 here. Okay. So they said that around 57% people say that we are familiar with the Qiskit. And some of 8% people say that we are familiar with the circ. Okay. And 10% people said that, okay, then we are using other thing and you have an CUDA queue. So these are actually, we can use the access the hardware, whereas the CUDA queue is from the NVIDIA. So there we use the your classical resources like a GPU or CPUs. Okay. Now we ask one of the question is that how it is important, how important is it for you to have a single unified platform? So why do we require a single unified platform? As I told you, right? Now the purpose of the Quniverse we came with is that you see people should not worry much about which hardware we have to use. Okay, so that is the one thing. So I will speak about it in the next slide. So many people say that we actually require require a unified platform. Okay. Now, and many of the people, 70% said that we are actually beginners in quantum computing. Okay. And they said that we require these kind of features in any unified quantum platform which are available in the market. Okay. So the answer for those kind of questions is from CDAC Bangalore is Quniverse. Okay. Now, what is Quniverse?
Excuse me, sir.
Yes.
Just a request to hide that bar at the bottom so that we can read the complete slides.
Okay. Thank you.
Yeah. Thank you.
Yes, I think I can hide it. Yes. Okay. Okay. Yeah. So you see the what is Quniverse? A Quniverse is an unified platform. Okay. What do you mean by unified platform? So as I told you, right, we have multiple hardware. Now users like you or the application developers like you need not worry about which hardware is at the back end. Now you can use any kind of a backend. Now you can use a superconductor based quantum computing, photonic based quantum computer, neutral atom based quantum computing. You can access anything. Okay. But still you should not worry much about your what kind of a code language I have to use. So that is a solution here. It is an integrated platform. Okay. For designing, simulating, and executing quantum algorithms on different kinds of quantum hardware platforms. Okay, like as I mentioned to you, all these various QPUs. Okay, and not that. See, for example, I mentioned to you NVIDIA CUDA-Q. Now, this is not an hardware, means quantum processing unit, but it's a classical resources. So you see, many of the people to start with, they don't want to work on a real hardware also. You see, they have certain model there, so they want to see whether my model is working well or not without any kind of a noise. Now, the issue with the present day hardware is that you have a lot of noise, right? So even if your model is very well, but because of the inherent noises in the quantum hardware, now your results may not be matching with your theoretical predictions. So what people try to do is that initially they will try to simulate it on the classical resources, right? So in the Quniverse, it can run on CPUs, GPUs, FPGAs, and vector cards. Okay, so you choose whichever accelerator you want. You can select that and you can work on it. Okay. And at the heart of the universe is something called quantum software development kit. Okay. What is this? So it is it is actually the heart of the universe, which provides the different libraries. Okay. So different libraries for you to optimize the algorithms and to access the different kinds of algorithms. So you have an inbuilt quantum algorithms, which you see, I saw the schedule here. So people are talking about quantum teleportation. So those things, right? It's already available in the Quniverse. So once you learn what is the quantum teleportation, so you can actually go to the Quniverse and you can actually see that, okay, how the Quniverse can be useful for learning quantum teleportation. Okay, maybe briefly I can show you how the teleportation will work. And anyway, I thought in this particular session to show something on a Grover's algorithm. Okay, using the Quniverse. Okay. Now, this is a brief introduction about the Quniverse. Okay. Now, so some of you could be from the computer science background. So those who are actually interested, right, how the Quniverse is working, I just want to briefly tell the basic architecture of the Quniverse. Okay. Now, Quniverse, you can write your own codes. Okay. Or you have a visual circuit builder. So you can just drag and drop your circuits. Okay. So that is the role of here, okay, the user. Then what happens is that the universe will convert into quantum intermediate representation called quantum assembly language. Okay. So it's called QASM for in a shortcut. So it's a QASM language here. Then based on whatever hardware you want to use or whatever classical resources you want to use, so there is a quantum transpiler will convert into different languages. So as an user, you don't need to do convert these things. You don't need to write in the Qiskit, Sir, CodaQ, or any other platforms. Okay. Now you just write your code once, or if you're not much interested in coding, you can actually drag and drop it. You the circuit, you can build the circuit. Then the quantum transpilers will be converted into converting the QASM language into whatever the language you want. Okay. Then if you want to again now here if you want to use the classical resources like a CPU, GPU using the HPC Slurm, you can actually run it on these various classical platforms. Okay, so basically you're doing the simulation. Then if you want to run it on a hardware, okay, you can actually use the API or the cloud providers. Say for example, you can access the Starmon 7 or Tuna 3, the real hardware. Okay, there are the IBM systems. These are the real hardwares. Okay, and as you are already aware, so there is something called a national quantum mission is an ongoing thing happening in India. So people are actually developing indigenous QPUs. Okay, so the idea is to integrate this national quantum mission hardware into QUniverse. Okay, so starting with the photonics, so we are already part of certain projects like a photonics hardware and a superconducting based hardware. Okay. See, superconducting base, basically, we are having our own quantum reference facility. Okay, so we will be having it in maybe 9 months time. So where CDAX quantum, our own QPU, will be integrated into this particular QUniverse. Okay. Okay. Now, to just once again summarize what the QUniverse is about. So it has a unified interface and it's a platform agnostic. So it can work on different hardwares, different classical accelerators like CPU, GPUs, FPGAs, and vector processors, and you have inbuilt libraries, okay, and optimized algorithm libraries. What I mean by optimized algorithm libraries, say for example, you might be familiar with these well-known algorithms. Okay, now we'll have our own dynamical oracles. Okay, the optimized versions of the various other algorithms are inbuilt in this particular QUniverse. Okay, and as I told you, you have an hybrid uh, problem. Okay, now we have a quantum hybrid classical quantum workflow which is already available in the QUniverse. Okay, now for people very new to quantum computing or maybe the researchers who want to work on certain other aspects, which you see, for example, you want to work on quantum machine learning, so there is already resources available in QUniverse for you to access them. Okay. Okay, so this is the final thing about QUniverse. Okay, so now let me actually access to QUniverse. Okay, I think still the screen is visible, right? No issue. You can see the QUniverse, right? You can see the login page of the QUniverse.
Yes, we can see.
Okay, fine. Thank you. You see, basically, you can actually go to quniverse.in. Okay, now you can actually go to the register and you can actually register. Okay, you can just tell the brief details about yourself and you can actually directly, you can register and you can log in. Okay, they already have the account. So let me log in. Okay, fine. So this is the, once you log in, right? So this is the page you actually see here. Now this is what I'm actually saying. Okay, so you see, this is a visual representation of how do you build a quantum circuit. Now, in the earlier session, you actually learned about different gates, right? Now, here you can actually see that, see, there are 3 qubits, okay? So this is an you can see actually a pellet here. So these are the gate pellets. Okay. And you can actually have see these, you can implement your own circuits in this here. Okay. So let us try it out what you have learned in the last session. So what we'll do is that let us start with one qubit. So you see here, you see you're on the left side here, you're actually seeing Q0, Q1, Q2. So these are the quantum registers, and C0, C1, C2 are the classical registers. Okay. Now let me just have one quantum qubit and one classical register. Okay. Yes. Now you see here we have a qubit. Now by default, the state is always a ket 0. So basically it starts with the qubit 0 state. Okay. Now, if it starts in the 0, okay, you have one widget here. You can see here, let us see the state vector. So it says that the initial state is 0, right? Now, if you apply a NOT gate here, so the state will flip to 1. Right? So this is what actually you can see here. Now, you see, state vector can actually have you see, it's actually a complex, it can have a complex amplitudes. Okay. So one thing you can actually look at is that you can look at the probability distribution. So instead of a NOT gate, so let us apply a Hadamard gate. So what does the Hadamard gate does? So Hadamard gates actually, when apply qubit 0, so Hadamard gate apply in a qubit 0, what will happen is that you will have an equal superposition of 0 and 1. Okay, so that is what you can actually see here. So 50% when you measure the state, there is 50% of the chance that the final state will be 0, 50% of the chance you will see the final state 1. Okay, so this way you can actually visually see that. Okay, even without running the circuit. Okay, so you can actually have run it. I will show you that. See, I'm not running the circuit at all. But even before that, you see, you can instantaneously see that. Okay, so this feature will be available for up to 6 qubits. Okay, see, now let us you see here you have the Pauli Y gate, Pauli Z gate, now which you actually listened in the last session. You see these are all single qubit gates here. You have a rotational gates, and you have a unitary gate here, and you have multi-qubit gate. Okay, so it's a control knot. Maybe let me add one more quantum register and one more classical register. So this will create a quantum entanglement. Okay, so this will create a quantum entanglement. So it creates a state. So basically this is a state. Okay, you have a 0, 0 and 0, 1 with an equal superposition. Okay, and the probability distribution that you can see here. Okay, it's 50% chance that you measure 0, 0 and 50% of the chance that you measure 1, 1. Okay, now okay, so just here, right? Hadamard we are applying here. So let me apply a NOT gate before that. So what does a NOT gate does? So basically NOT gate flips the state from 0 to 1, and then you're applying a Hadamard gate. So what does it will give? It will give us equal superposition of 0 and 1, but with a phase. So it is ket 0 minus ket 1. Okay, and you have this normalization constant, right? Now, okay, you see here. So it's you have a phase difference, you see. So earlier when you applying without a knot, so when you ket 0, when Hadamard is applying just in ket 0, you actually have an equal superposition. Okay. Similarly, you have an equal superposition when Hadamard is applied on ket 1, right? So it's same, but one thing is that it's actually gives a phase flip to 1. Okay, that can actually be seen here on this particular widget. Okay, so these are the tools for the people who wants to understand how actually quantum computing is actually working it out here. See, for example, when the state is 0, when your input state is 0, the output will be 0 and 1. You see the size of the circle says that what is that amplitude. Okay, so for both of them it is 0.707. It's actually 1 by root 2. Okay, and the color red color says that there is no phase difference. Okay, but Now let us look at when the input is 1. Okay. Input is 1 is also the output is 0 and output 1 with an equal probability amplitudes. Okay. It's 0.707, which is 1 by root 2 again. Okay. But you see the phase difference here. There is a phase difference between 0 and 1. Okay. So in this way, you can actually use this particular widgets here. Okay. To understand quantum computer in a better way. Okay. Now this is all without even running your circuit. Okay. Now that is actually the thing we have to make use of the QNOS tool here. Okay. Now going ahead. Okay. So see here, when I'm applying a NOT gate, you see here, you see, this is what I'm saying, the quantum intermediate representation. So when you have a NOT gate, okay, so when I'm applying a NOT gate here, you see, you can actually see that it's automatically, the code will be written here. Okay. You don't need to write any specific code here. So it will automatically will be translated into open cosm code. You can see now how the NOT gate comes in. Now it can also be, see, for example, you can add one more Hadamard. Okay. Q. See, that could be vice versa. So instead of, you can actually drag and drop here, or you can write the code which will be translated into the gates here. Okay. Okay. Now here, now you see, as I told you, now from here, if you want to run it on an IBM's hardware or the Google hardware, you want to convert into Qiskit, it will automatically be translated into that particular language. Okay. Now, some of
phone आ रहा है कैसा तो उसका इशरत का फोन आ रहा है
okay.
Participants are please requested to keep your mic off. शाइस्ता मैम,
आजकल सालन बनवा ली चिकन का सालन ये तो हम बोले चिकन का सालन आंटी वो 2 टाइम का था वो 2 टाइम का सालन था क्या चिकन का ना आटा है गूंदा हुआ ना सब्जी कटी हुई है इधर आटा है अगर आपको आज नहीं आना था आंटी तो आटा वाटा तो गूंद के जाना चाहिए था ना आटा गूंद कर आएंगी तो आंटी सुबह रोटी बनी अभी के लिए रोटी के लिए पूरा आटा नहीं है अभी आपको हम नहीं कर सकते ना जी मैं जो 2 महीना से छुट्टी लीजिए मेरा तक नहीं
Thank you. I think I'll continue. Okay. Right.
यार मेरे को लग ही रहा था Sorry, sir. Very sorry. Sorry.
continue, sir. Participants, please keep your mics off.
Sir, your mic is off, sir.
Okay. Can you hear me now?
Yes, sir. Yes, sir.
Yes, sir.
Yes, sir, sir.
Yes, sir.
Thank you. Okay. You see, I hope the screen is shared. Yeah. Yes. Okay. You see, one thing is that this could be useful for like you have certain algorithms in mind and you can actually build your own quantum circuit. But people, you see, for example, in this session, you're actually looking at quantum artificial intelligence. Say maybe there you don't want to drag and drop your gates. So people like who wants to write their own codes, right? You can actually go to the Qiskit editable here, okay, and you can actually write your own codes, okay. So that is actually given, okay. Fine. So it is up to you what kind of features you want to use here, okay. Fine. And here you see in this particular palette, okay, this is a measurement gate here, okay. Now this one actually converts you measure your quantum state. So the state, you can actually read the classical information. Okay, so that is the role of this measurement gate here. And this is like a barrier gate. This is not a gate. This is actually a barrier to differentiate between certain parts of the circuit. Okay. Now here, right, what we can actually do is that, say, for example, if this particular gates, you feel that you use very often, right? You can actually make them as one particular gate. That is your own gate. Say, for example, my specific gate. Let me call my specific gate MSG. Okay. So this is my specific. You can actually save that. Okay. So you see, actually selected the measurement here. Okay. So let me. Okay. So let me select these things. Okay. MSG. Okay. You see, this one is your own gate now. Now, whenever you feel that, right, if you want to use it, you can actually drag and drop it. Say, for example, I want a jet gate. Okay. Then I want to use in my MSG. Use an MSG. Then apply some other gate. Okay. Based on your requirements, and you can again. So this is like your own pack of gates. Okay. So whenever you feel, you can actually use that. Okay. Now, let us say that now you want to run it, right? So you see here, now the codes will be automatically will be generated on the top right and the right side here. Then once you have your own circuit is ready, then you can actually choose any one of these things. You see, basically you can use the CPUs, you can use the GPUs, FPGAs, the QPUs. So let us take for example CPU. So this you want to run on a simulator. Okay, so you can use the resources which is deployed in the CDAC Bangalore. So you can use the QACC cluster. You can submit it. Okay. So, okay, you'll get a job ID. And then once it is run right, you can actually go to the jobs. And you can actually see that, okay, as of now it is queued, but I think it should not take much time. Yes, it's got completed. Okay. So this is certain gate. Okay. So this particular gate has this kind of probability. Okay. Now you see it is 0 comes with the 14% and 1 comes with this 85% of the time. Okay. So this is how the result will be coming here. Okay. Now you feel that, okay, maybe this is not the circuit which you want here. Okay. You can actually, you can see the code here. This is the circuit which you implemented. Okay. We are actually providing, you can actually access the photonic circuit also, which will be deployed very soon. Okay. Now you feel that, okay, I need to do certain other modifications. You don't need to again drag and drop or write your own codes for this. You can just go to the load circuit here. Okay. It will automatically generate it here. So you can actually see here what is there in this particular MSG. Okay. So this is a Hadamard and a NOT gates. Okay. So this is what is there in this particular your own set of gates. Okay. Fine. So this is what I want to speak about here. Okay. Now, okay. Maybe if you want to run a QPU, right, you can actually select. There are various quantum hardwares that are available here. Okay. Some hardware could be freely available, but some part, if it is coming from a third party, okay, you can actually see. Okay. This is the StarMon 7. You can actually run on it. Okay. So earlier case, we actually running on a simulator. Now it is actually, okay, unable to refresh token, please generate keyword for the profile section. Okay. Now, because there are third parties here, we actually need to generate this particular tokens. Okay. This is very easy. Okay. You can actually look into that. Okay. Okay. I will not do that point at this point. Okay. You can, that's a very straightforward. You just can generate the token. You go to this site, and if you once you click on generate, right, you get the API key to access on it. Okay. Okay, in the last part of the session, I want to talk about the Grover's algorithm. Okay, so what's the Grover's algorithm? Just to, okay. So I'm not going to the details of the Grover's algorithm here. I just want to show the how do QUniverse will help in understanding this kind of an Grover's algorithm and come up with your own algorithms. Okay, so what's the Grover's algorithm? So in simple terms, right? So Grover's algorithm will help in, okay, to find the target elements in unsorted database. Okay, so let us say that we have n states. Okay, so there are n qubits or n bits. Okay, the total states are 2 to the power of n. So out of n states, right? Now let us say that we require m target states are there. Okay, so m target states we need to find them. Okay, now classically, okay, right? So this is an order of n, right? Now Grover's algorithm, which is a quantum computing algorithm, okay, which it will gives in a it gives in a quadratic speed up compared to the classical algorithms. Okay, compared to the classical algorithms. What it does here is that, okay, so what I'm doing here is that, so these are my initial states. Okay, what my initial states? All the states, all the n states. Okay, I'm just writing an equal superposition of all the states. Okay, now that is where quantum computation will have an advantage to start with. Say for example, say let us take, there are two elements, 2 bits. Okay, so basically there are how many states will be totally? 4 states, 0 0 0 1 1 0 and 1 1. So one of the state is actually our target state. Okay, now we have to use the oracle approach or a query based approach. Say for example, if 1 0 is our solution, how do we search it? Okay, you go one by one and search whether it is a solution or not, right? But in quantum computing, in this particular Grover's algorithm, what we will do? Okay, okay, and mathematically what I'm doing is that I'm actually dividing it into target states and non-target states. Okay, see this image here. Okay, now this is our initial state. Okay, which is consists of both the target and non-target state. So in the case of 2-bit case, you have this state is equal superposition of all the states. Okay, and it is very close to the non-target. In this case, it's a 1 0 is your solution, right? So if you're writing in the summation of all the states, only one target state and 3 are non-target states. So you can actually see that if you're actually decomposing into this state into all the states, okay, the target and non-target states. Okay, okay. What is the idea? The idea is that I have to do some operations on my initial state such that my final state, when I want to measure the state, it should be closer to this particular site target state. Okay, right? Now, so just to once again just look into that. You see, for example, to start with, you are having an equal superposition of all the states, right? Okay, maybe I will. Okay, no. Yes. So let us look at these 2 qubits. Okay, I want to search a 1 0 here. Okay. Now this is the quantum circuit, the Grover's algorithm. When you write in a circuit implementation, right? So this is how it looks like. So basically what is actually happening here. So let us look at this particular feature called a debug. Okay. So debug here, what is your initial state? The 2 qubits are in 0 0. So one qubit is in 0, the other qubit is in 0. So total initial state is 0 0. Now what I'm doing, I'm actually writing all the states in equal superposition. How I am doing that? I'm applying Hadamard on both the qubits. So I'll just see here. Right. See here, all the states are in equal superposition. Right. Now, if you're measuring at this point, if you measure the qubits, right, what will happen? 1 0 has a 25% probability. So that means that it's 1/4 probability. So remaining non-target state will have a probability of 3/4, 25%, 25%, and 25%. So if you're measuring at this point, so you'll have actually 1/4 probability only. But we want the final targets to be closer to 100%. How do we do that? So that is where Grover's algorithm will help us. Okay. So first of all, there is something called a oracle here. So what does the oracle does? Oracle tells that 1 0, it gives a phase flip to the 1 0. If you look at here, you see, it's still in the equal probability, but just look at this state vector here. You see, for only 1 0, it is actually giving a phase flip, right? You see here, before applying the oracle, there is no first flip. All of them are in equal probability distribution. It equals over distribution. But once you apply the oracle, okay, so that's why it's called as a query-based algorithm. So now it says the 1-0 is the solution. But how is it saying? It actually giving a phase flip. But if you measure at this point, still it is a 1/4 only. So oracle just giving a phase flip, right? It is not actually, it is not making it 100%. So the role of that is comes to the diffuser. So what does the diffuser do? Diffuser will actually amplify this particular 1-0 state. Okay. Now that is the role of a diffuser. See here. Once I do this thing, you see the 1-0 has a probability amplitude of 1. That means that the probability distribution comes to 100%. Right. Now this is how the Grover's algorithm is working. Now to understand this one, right? Now that is what I want to show here. Now what is the Grover's algorithm doing here? The Grover's, your initial state, right? Your initial state is this one, which is an equal superposition of all the states. Then you are doing a reflection around. This is the role of an oracle. So the oracle is actually saying that, okay, so it is giving a phase flip to the site target state. So that is what you see. Nothing will happen to the phase of the non-target states. Only the phase of the target states will get flipped. Okay. Now then we apply the diffusion operator. What the diffusion is doing? The diffusion is actually doing here. It is actually reflection around this particular site. Okay. So that's the role of a diffusion. Okay. Now that means that it is actually amplifies that particular state. Okay. It is going closer to the site target state. Right. Now, in this particular case, in the previous case, this happened only once. But if you look at here, right, many of the cases that it will not be closer to the site target by one iteration. You have to do multiple iteration. So you have to do the same operation. You have to do the reflection around sign on target and again do the diffusion operation. So you have to do the k times. Okay. So this k is actually where you do the square root of total n. So that's a capital N. Okay. So this is how you have to do the multiple iterations to come closer to the site target state. Okay. Now this one, you can actually see in the Quniverse. Let us look at before finishing the session. So let me try for 4 qubits. Okay. So the solution will be 1 1 0 0. Okay. Now this is the load circuit. You see here. So these many times you're actually applying here. See your initial state. So this is the oracle part. Okay. So this is the diffusion part. Then one more oracle and then one more diffuser. There one more oracle and one more diffuser. Say this is what I'm saying earlier. For these things, right? What you can do is that. Okay. See here, the final state is 1 1 0 0. Though this is not 100% probabilistic. If I say 100% deterministic, you're coming closer to the 97%. Okay. Now what we can do is that you can actually use the manage option as I told you earlier. So not the manage. You can make your own this one. So this is nothing but a Grover's operation, both the oracle part and diffusion part. So you can call it as a Grover's operation. Grover's operation. Here you have oracle plus diffuser. Okay. So this one, this way, right? You can actually get them already. Okay, I think I already. So let me use a different name. So let me calling as G4 qubit system. Let me call G4. Yes, if you use the G4 here, so then you can actually delete all these gates. See here, instead of that one, now you can apply this G4. How many times we need to apply? 3 times we need to apply. So So you apply just 2 times. So what is happening? It is coming to only to the 90%. If you apply only once, if you apply the Grover's operation only once, it is just 47%, right? So apply once again. Actually, we require 3 iterations for it to be have an optimal result. Sorry. Yes. If you see here, now it is the optimal result. Now it is 96%. So Grover's algorithm says that you require 3 iterations. Let us go for 4th iteration. Okay, we feel that it goes more. No. You see here, it actually the probability actually decreases 58%. So the optimal is actually 3 iterations only. So in this way, right, you can actually understand Grover's algorithms, you can understand different other algorithms, and you can implement your own circuits. So you can actually see that, you see, using Quniverse, you can actually see that what is the best, how your algorithm is actually working out. Okay. In this way, Quniverse will help you in certain things, like implementing your own algorithms and applications, and to run it on different kinds of classical resources, quantum resources. So yeah, so yes, so I hope just try to use it. Okay, so maybe people are familiar with the different kinds of tools like Qiskit, Circ. Okay, so this is also some kind of a tool which can be helpful for you. So you can choose which one suits the best, and you can work on that. Yeah. With this thing, right, I think I can actually stop. Okay, so initially to start with, all of you will get 150 credits here. Okay, so yeah, so based on your working, right, the credits will be decreased, like for a CPU it will be decreased by 5 credits, GPU 10 credits, QPU 2 credits. Yeah. And you have many more features here. You can just start exploring them. Okay, you can have a documentation. You can actually see how to use, what features are available. Okay, you can have an own troubleshooting problem for FAQ. If you have any still in issues, right, you can always write to us. Okay. With this, I think I can stop my lecture. I'm happy to take answers. Thank you.
Hello, sir.
Yes.
Yeah, this is Ashish Vanmai from VCET Vasai.
Okay.
Yeah. So, the students are also allowed to use this platform, or is there any restrictions that don't?
No restrictions. Everyone can use it. This is for free to start with. Yes.
Okay. And for academic purposes, are there any specific packages that you provide to the institutes?
Yes, we do provide. I think maybe you can just write to us. Okay. I think based on your my requirements, I think the team will coordinate with you.
Okay. Thank you, sir.
Thank you.
Participants, yeah, you can ask your queries.
Yes, I think yes, there is one question. Yes, it is a free to start with. Okay, I think 150 credits will be free. Okay, maybe once it is done, right, I think then we have to see how people can actually purchase that. But to uh, to for everyone, you will have an 150 credits of free, and we are actually thinking that you see, for every month we have to we will give certain credits for free. So that was the idea, but still we need to see how we need to plan.
Hello, sir.
Yes.
Sir, good evening. Really, it's a very good session, sir. Thanks a lot for your presentation and the tool what you have introduced. So I'm very new to this quantum actually. So out of curiosity, I have joined in this FDP to learn more on quantum. And in that curiosity, I would like to know what about quantum image processing and its application part in this tool, sir.
Ma'am, actually, I didn't show that, but you see, I will just share it once again.
Yes.
So, yes. Actually, people are working on quantum image processing and machine learning, ma'am.
Yes,
Here, if you look at, even the algorithms, you have a quantum machine learning. So you have a QSPM, QKNN, QNN, quantum neural networks, QPerceptron. So people actually using quantum machine learning, ma'am, for using a QUniverse. Quantum image processing will also you can do, but only issue I see is that you see if you're using a classical resources, so there is a restriction on uh, how many qubits you can actually access. So that means that your data size will be lesser. So that is the one issue I see people actually face it. So you require a real quantum hardware to actually scale it up. But I think you should actually use quantum computing for your quantum image processing, ma'am.
Sure, sir. Sure.
Thank you. Thank you for your expert.
Thank you, sir. Thank you so much.
So participants, any other questions?
Okay, my email ID, right? It's Naresh
Yes, sir.
Raghava. Yes, sorry. Naresh Raghava at the rate of c.in. So my name is here. So without any space, you have Naresh Raghava at the rate of cdac.in is my email
Okay,
ID.
sir.
Yep.
Okay, sir. Okay. Okay. So, sir, actually, I'm also very new to this field, right? But I found it very interesting. This, like, we can, sir, you have given an example, like, how it can be used, like, GPUs and CPUs and FPGAs. So,
Yes.
can you just give me, like, how we can use it? Like, can we can simulate those GPUs or FPGAs programs also over there? Is it something
Yes,
like
ma'am.
that?
You see, basically, when I say the programmings, you have your own quantum circuit. So then you can
Hmm.
choose a backend. So you can use the GPUs, see for
Okay,
faster
okay,
running or for parallel processing. So you can
okay.
actually see the backends. So you can use
Hmm.
our own. These are from the CDAC. So
Hmm.
you can use the CDAC GPUs and vector
Hmm.
cards.
Okay, okay, okay. Thank you so much, sir.
Thank you. I think
Okay,
anyway, I think Mr. Sachin, I think will be presenting
okay,
on
sir.
Saturday. He will speak
Okay,
more on quantum machine learning.
okay, sir. Okay, yeah, yeah, yes, sir. You have given a topic. Yes.
Yes.
Sir, can you
So,
please display your mail ID, please?
Okay, maybe I
sir,
will just
if
yeah.
can you write in a chat box? Is it possible, or should I write? You
Sure,
can
I think
check.
chart is only available during the meeting. It says maybe it's Naresh Raghav at the rate of cdac.in. You can just type it, ma'am. I think it's not available to
Continuous,
me.
no?
Yes,
Yeah.
continue.
Narendra Raghavan at the rate.
Naresh Raghava.
Hmm. Hmm.
Yes, more videos on this platform. Actually,
See that. Hmm.
yes,
Hmm.
sorry, I think
See
there's a
that
question.
dot in, no?
cdac.in. Yes.
Okay.
I think some Dr. Sandeep has asked a question, more videos on this platform. You see, recently, I think 1 month ago, we actually came with webinar series. I think Raghava, I think there is a double RE, ma'am. I think only one RE should be there. Yeah.
Okay, okay. I'll
Yes.
correct.
So yeah, we have a QUniverse webinar series and QUniverse. So where we actually extensively covered many of the algorithm, including quantum machine learning and quantum chemistry kind of problems. So people can actually go through YouTube videos. Okay. Yes. So yes.
Okay. So participants, you have more queries? Okay.
Once again, I request all the participants to turn on the cameras so that we can take a photograph, screenshots with the uh, sir.
Sir, second, please, one more doubt, sir, please.
Sure,
Yes,
ma'am.
Yes,
sir.
sir.
Please,
Sir,
please.
this is Sudha. This is Dr. Sudha from Shastra University. Already I just asked. Sir, regarding this quantum image processing and all, do you have any YouTube links, sir, or YouTube videos from
I
CDAC?
think CDAC, I think, yes, ma'am. I think you just look into, I think he didn't specifically target on quantum image processing, but he covered certain other aspects of quantum machine learning. Just look at QUniverse webinar series, ma'am.
Webinar series,
QUniverse
okay.
webinar series. Anyway, Mr. Sachin will be coming on Saturday. Maybe he
Yes.
can throw more light on that.
Right.
Yes.
Thank you so
Sir,
much, sir.
we
Thank you.
sir, we have one more question. Can we say that Q University India is Q is kid?
Yes, actually, okay. So we are not just following the Qiskit. So basically, the idea is that, yeah, in a similar way, actually, it is like the interface and it will be closer to the Qiskit. But the idea is not just restrict to the Qiskit or IBM hardware. The idea is to have all our indigenous quantum hardware accessible to the Quniverse and external hardware also. So that's the idea.
Sir, is it free downloadable or any amount should be paid for the sessions?
Ma'am, so the which one you were talking, ma'am? You were talking about the Quniverse webinar series. That is for free. Quniverse is also free of cost. Like you can actually enter it, but only issue will see that once the 150 credits got completed, then you have to purchase certain credits. But otherwise, it's free. It's India's language agnostic platform. Yes, I think Vishwanath Kuchi, Mr. He actually put in right thing. It's an agnostic platform. Yes.
Previous to the IBM Qiskit, it is free, sir. After some time later, now we have to pay amount to use the sessions
Yes, ma'am. I think,
computationally.
yeah. So to just put for everyone, right? You see, Quniverse is funded by the MIT, okay, because CDAC is actually an autonomous organization under the Ministry of Electronics and Information Technology. So this is for people of India, right? So only thing is that it will be running on hardware resources. The cost, you see, whatever the cost incurred to run the resources. So it should not be much costlier, okay? But what we also feel is that every month, there should be certain credits should be given free to all the users. Okay. But if people are extensively using it, maybe there they have to pay for the resources.
Okay, sir. Thank you.
So Ashish sir, can we take a photograph?
Yeah, participants, once again, I request you to please turn on your cameras so that we can take the screenshots. Yeah, thank you, everyone. Shaista ma'am, you can conclude the session.
Okay, sir. So, Naresh sir, thank you so much for like I approached you very end moment but like you and your team has given us a time and like you have shown a very interesting part of it. Like this is a very good platform where we can like before implementing we can test our design flow and then we can implement. So thank you so much, and I think so question answer session also indicate like the participants are also like found it very interesting, and everyone is interacting also. So thank you so much. So be in touch, and so we can further also we can work on this topic also. Thank you so
Thank
much,
you,
sir.
ma'am. Thank you.
Thank you all the participants for attending so late also. Thank you everyone.